So now we're going to get both days, which is great. This is the first time in all these times that I'll actually have remembered. Okay, so, all right, we are now on to page 55, believe it or not, which is amateur radio practices and station setup. And why did we spend all that time doing Ohm's Law yesterday? The reason we spent all that time doing Ohm's Law was because Ohm's Law is really, really important. And what I've found is that in my professional life, doing work, I have found that 90% of the electrical problems that I encounter are actually applications of Ohm's Law. So we're going to spend a little bit of time on this one, probably more so than most people would, but I think it's really important. So here is a battery, and we're going to put 12 volts. All right, so this is our car. And now we're going to take this and we're going to use a radio, put it way over here. And it's going to connect to our 12-volt battery. Okay, so here's our 12-volt battery. The radio, when it's transmitting, is going to draw, let's say at 100 watts, it's going to draw 20 amps. This is actually fairly common for a 100-watt radio. So let's do a little quick math here. And if we're doing 12 volts and we're pulling 20 amps, what is our power? All right, so we're getting right back into it. P is equal to I times E. We're going to draw that little circle. And it is then P is equal to I times E. It's equal to 20 times 12 is 240 watts. All right, how many watts output did I say that our transmitter was?
100.
Okay, so where does the extra power go?
Back to the battery.
Nope, does not go back to the battery. This is power that's being used. It is being used. There's 140 watts that is being used somewhere or shows up somewhere.
The radio's using it.
Yeah.
About the heating cost?
Yeah. Okay. So you've got the electronics inside the radio that run no matter what happens.
The heat sink.
You've got a heat sink, and the heat sink is working there because of efficiency. So typically to run and actually generate 100 watts of RF, right, you would typically have to put in somewhere between 180 and 200 watts of power to get 100 watts of RF out. The extra 100 watts is lost in efficiency. So your efficiency would be 100 divided by, let's say, 200 on the transmitter. You'd be a 50% efficient transmitter, right? Not so great, but that's what you got to get. That's what you got to do to have a to actually generate RF. And so your efficiency will essentially cause you to lose 100 watts in heat, let's say 40 watts in the electronics. So that's 140 watts, which means your radio has a heat sink, and it does get warm, right? Even a transistor radio will get warm. All right, so more importantly, though, let's say that we have a rather thin cable, and the thin cable has a resistance of 0.5 ohm. And that's the entire loop, right? Because you have to go out to the radio and back, and you measure it at 0.5 ohm. So if we were to look at this and say that the wire has a 0.5 ohm resistance, we're going to go back to E equals I times R. All right. So how much current did we say we're drawing?
20 amps.
20 amps times 0.5 ohm. How many volts are we losing in the wire?
10.
2.
Okay, how many volts did we begin with?
10.
120.
No, we began with 12. All right, so
12
how much voltage do we have left to run the radio?
10.
2.
They have 2 volts.
2.
Yeah, that's not enough to do this. So that is why you want to take this wire and make this as heavy and as short as possible, because the way that wire is made, the way that wire works with DC is that there are 2 things that function into wire. One is its cross-sectional area, because the current is distributed at DC throughout the cross section. So the bigger the cross section, the bigger the pipe, the more area there is for current to flow and the lower the resistance. The other one is how long it is. It's basically going to have a resistance that's proportional to its length. The longer it is, the worse it's going to be, the higher the resistance is going to be. So if you have, let's say you bought a 50-foot chunk of cable and you just don't want to cut it, you know what? Go ahead and cut it. If it's too long, cut it. Because if you only need 10 feet, you should only use 10 feet, because otherwise you'll just be incurring voltage loss in your cable.
Are most of the manufacturers like Yaesu, Kenwood, are they going to give you a piece of wire that's usually fairly accurate? Or
They're going to give you, well, they'll give you like a connector with a 10-foot cable, and it's usually like a number 10. That's a pretty heavy cable. The problem is if you need to extend it and say you need to go 30 feet, you know, you may have to look at that. And this is the same reason that people who put in high power stereo systems in their cars end up putting in big fat cables, because at
Usually,
DC,
usually I use a 0 gauge for my system.
a what gauge?
0.
0. There you go. 0 gauge is huge. And the reason you're using it is because you have so much current pull that you don't want to have voltage drop.
Got a typical 100-watt radio. I thought I read somewhere that they can draw up to 28 or 30 amps.
It's usually max is about 22.
22.
That's typically what they rate them at, 20 to 22 amps. All right. So
for this example that you drew up, you said it was a car.
It can be anything. It's just,
At the beginning, you said it was a car. So would that limit us to a 50-watt for a
no,
mobile radio?
no. It's, I mean, I've run 100 watts in the car. I mean, a lot of it is then dependent on, you know, if you're pulling a lot of power, your charging system, because you're running it off your battery. So, you know, if you park somewhere and you run the radio for a few hours, you might end up with a mostly dead battery that isn't capable of restarting the car.
Unless you use a capacitor or a second battery.
Yeah, then
Yeah.
you use a second battery. Exactly.
Now,
bring
how,
it to this.
now how do you get to calm the engine noise?
We're gonna get to that.
Okay.
We're gonna get to that. All right. So when choosing a power supply, check the voltage and current ratings of the supply. Okay. So what must be considered when you're picking a power supply? You have to consider the efficiency of the transmitter, which we talked about, receiver and control circuit power, and power supply regulation and heat dissipation, because power supplies are not 100% efficient either. So in order to run a radio that is 100 watt radio, which will pull about 20 amps, you would typically go with a power supply that's good for at least 30 amps, just to give yourself a little bit of headroom. How can a computer be a part of a ham radio station? Well, as I was showing a little while ago, you use it for logging of contacts. You can actually use it for generating and receiving Morse code, because a computer has the ability to run a program that sends and receives Morse code. And something that I can't do in my head is digital signals. I can't generate or receive digital signals in my head. All right, so you can also interface a computer to a radio. So here's your computer, and here's your transceiver right here. Okay, so you have a couple of things that are necessary. If you think about your computer, you have a microphone. You also have a speaker, sound card or speaker. All right. So if you think about a transceiver, a radio, you have a speaker and you have a microphone. Okay. So if you wanted your computer to do the job of talking into your radio, essentially you would take the speaker from the radio and go to the microphone of the computer. And then you take the speaker of the computer and go to the microphone of the radio. So basically, the computer is now doing the talking. But then you need one more thing, which is essentially like a relay, which is the push to talk. So somehow the computer has to be able to enable a push to talk signal to key the radio. So that being said, if you think about this, how does your computer send audio to the radio? Right here, the speaker output of the computer goes to the mic input of the radio. How does the computer receive audio from the radio? The speaker of the radio goes to the microphone of the computer.
So I was reading this the other day and it was just confusing me because I never use mics. Mics do have an input.
Yeah.
Okay. Just because it just didn't compute with me. I was like, an input on mic. Wouldn't you think it'd be an output because you're speaking into the mic? But yeah, that makes sense.
No, it's a
now.
mic
Good.
input. It's a line level input. Okay. So what does a sound card do? All right. So what a sound card would do is essentially take these physical things right here and essentially turn them into something that is an electronic device. And that can be an internal sound card to the radio. I love having that. That means you just basically hook up in your transceiver and computer. If you have a sound card here inside the radio, what you do is you hook up a USB cable and you're done. Usually the sound card will also contain a push to talk button or the ability to do that if it's inside. Sometimes the sound card is not inside and there's something known as the most common one, most popular is called a signal link, made right here in the state of Oregon, which is an external sound card. So that's a USB cable. And then it connects to your transceiver. And you have your audio in, and then your audio out, and your push to talk. So that's an external sound card. They work great. They have nice little knobs on them so you can adjust volume levels and things like that. Okay, next. All right, in an amateur station, there's something called RF. What does RF stand for again, everybody?
Radio
Radio
frequency.
frequency.
Radio frequency. Okay, so every piece of wire can act as what?
An antenna.
An antenna. Which means if there's RF floating around, your wires can all act like antennas. So if anyone has ever noticed on their computer power supply, you have something that looks like this on the cord. Anyone ever seen one of these?
Yeah,
All right. Any idea what's inside that?
fuse.
It is not a
Ferrite.
phase. It is a ferrite. It is a ferrite.
Oh, okay.
All right. So what a ferrite is a donut. Usually it can be solid or split that you can basically pass a cable through. And this material right here is a combination of glue and iron powder and possibly some nickel and other things. So basically what they do then is they form that, they take glue and iron powder, form it into a shape and bake it. And this is now essentially a material that is a ferromagnetic material that is susceptible, very susceptible to magnetic fields. So what it does is you essentially choose your mix. This iron powder could also be nickel and some other things, depending on how you want it to react. And what happens is that as energy is traveling down this wire, it generates magnetic fields. The magnetic fields concentrate inside this material. This material is actually susceptible to certain frequencies because Well, that's what we're trying to catch. Let's say that you have a piece of wire here, and then you have your computer. Your computer does not want to see RF energy getting into it. It will cause all kinds of problems. Trust me, I know. So computer in the ham shack is a great thing, but a computer is very susceptible to RF coming in through the power supply. It'll cause it to lock up, and it'll cause it to sometimes shut down. And I know because I've done it many times. So basically, if this power cable is carrying RF right here, which it shouldn't be, but it happens to be an antenna, and you're transmitting, as it's traveling, it's generating a magnetic field. The magnetic field essentially gets trapped inside this ferrite because it's really, really conducive to magnetic fields. It's very susceptible to magnetic fields being trapped inside, and they basically will circulate and come off as heat. So how much of the magnetic field shows up on the other side? If you've killed the magnetic field, you've basically killed most of the energy, which now means that your RF energy is choked off. And this is actually called a choke. It's a ferrite choke. And that's what it does. It actually chokes off the RF energy, which chokes off the signal getting into your computer. DC passes right through. You have a DC power supply, so that's a good thing to use. And that's known as a ferrite choke.
So that's how you would kill the engine noise with a ferrite choke.
Well, that's another thing. Because engine noise, if you think about it, what is engine noise caused by?
The alternator charging the
Well,
battery, which is
That's
backfed.
part of it. What else is engine noise caused by?
Spark plugs.
Spark plugs. You have
Yeah,
going off inside the engine. So you have two different kinds of noise being generated inside the car. Actually, many more, because you also have the microprocessors and such that are running inside the car, and you have RF being generated by those as well. So let me see if I'm still, oh, I can turn off the video here. Stop video. I don't need to see that. So what ends up happening is that you have multiple different flavors of noise being created, right? So you have alternator whine, which sounds like zzz. And as you speed up the engine, you hear the alternator whine. So you have the alternator whine. But then you also have spark plugs. Okay, and the problem with spark plugs is that a spark ideally is going to be a square wave as it's generated internally, and it's a very short duration. And a square wave, as it actually turns out, if you do a mathematical analysis on it, actually contains a whole bunch of different sine waves, which is why lightning, when a lightning strike happens, it generates noise on all frequencies, because a lightning strike is basically just a pulse. So it generates these frequencies and lots of others, and even faster, higher frequencies. It's a terrible mess. A spark plug, when it fires, makes a terrible mess. Now, it's also true that that noise that's generated is amplitude modulated. If you've ever noticed, if you're in a thunderstorm and you're listening to the AM radio, you'll hear crackles every time there's a lightning strike somewhere. On an FM radio, you will not hear that. And that is because FM radio listens across an entire band of frequencies. And what did we say about lightning? Lightning causes noise on all frequencies. So what happens is that temporarily all of these frequencies jump up in amplitude. Well, your radio internally knocks these off and lowers that value. So essentially that noise occurs across the board. And because of that, FM radio is essentially immune to lightning strikes, static crashes. And that's why you would not typically hear that if you're listening to an FM radio during a thunderstorm. Okay. So as far as knocking those out, we have something in the radio called a noise reduction circuit, typically if it's an AM based radio, so single sideband. We have noise reduction, which can be like a digital signal processing that can serve to listen for some of the sounds that are coming in that shouldn't be there. But then we also have something called a noise blanker, which we're going to get to. And essentially what a noise blanker does is it looks for periodic pulse noise, pop, 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 pop coming in from the spark plugs. And whenever that pulse happens, it reduces the gain of the receiver, so that it also unfortunately reduces the gain of the receiver that's listening to what you're listening to, but at least you don't have the objectionable pop, 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 pop coming in. So again, that's called a noise blanker. All right, so which of the following conductors provides the lowest impedance to RF signals? There are some other choices that are given. The one that you have to answer, the one that you have to know and why, is known as a flat strap. Okay, so there's an interesting feature of radio frequency energy, and in fact, all AC. All right, so here's my cylindrical conductor, and we're going to look at DC. All right, so direct current basically will distribute as current flow. So remember, current's just electron flow. DC distributes across the entire surface area. So whatever the area is, it basically is even throughout. All right, if I were to draw this with AC now, what I would find is that my current distribution would be that it's very, very low in the middle and increases as you get to the outside, and that the highest concentration of current flow is on the outside. So this is true at 60 hertz. This is true at radio frequencies. The higher the frequency you go, the more pronounced this is. This is known as the skin effect. So the question then is, which would provide, as you can see here, because AC likes to travel on the surface of a conductor. If you had the same amount of metal, how would you maximize the amount of surface area that you have? You take your cylindrical thing and you pound it flat. It's the same amount of material, but now you have all this surface area. And that's why if you're looking for something to carry RF energy, like move it somewhere, it's not going to be a coaxial cable, for instance, though. But if you're trying to do like grounding or something like that, and you want to be able to conduct RF energy, that is why you would use a flat piece of copper.
And the field that they produce is not as big of an array and a flat strap as well. Is that what you're saying?
No, actually, what happened? I mean, we're actually talking about how to carry RF current.
Oh, RF itself,
Yeah,
not the external effects of
not the fields. Basically, if you've got, for instance, a piece of equipment here and a piece of equipment here, and you've got a grounding bus bar that's tied to ground, and you've got a connection here and a connection here, you typically want those to be a piece of braid that's been squashed flat. Tinned braid works great. Solid copper, like a piece of copper flashing, works really well. And again, the reason being that you actually want to provide the lowest impedance to ground. And because it is based on the surface area, this provides much more surface area than a cylindrical conductor.
God, is that why like
For
the
RF.
generators have those flat grounding straps?
Yeah, that's why everything, anytime you want to do RF grounding, that's why.
Like on antennas?
Uh,
Antenna?
well, it's more for equipment grounding.
Okay, but doesn't the book say something about tying all the grounding to a plate, to a common plate, or?
Well, that's what this would be.
read that.
That's
Okay.
what that would be.
If we ever seen a flat plate, it'd be a dead giveaway of AC current, and we could probably figure out what it's connected to.
Often, yeah. I
Okay,
mean, and this, I just consider this to be like a bus bar. That's usually, that can often be like just a block of copper or aluminum with a bunch of holes in it. And you just basically tie all your conductors, all your grounding conductors right to that. And then you bury your ground. Okay, what should the negative
So
return?
You,
Oh,
you
go ahead.
would want the ground wire from the bus bar to be quite a bit larger than any of the wires leading into it, right? So that it can
I would,
take all
yeah.
of that current without too much trouble.
Well, honestly, hopefully you don't have a whole lot of current because we're not dealing with current in that sense. You know, I mean, this is not like we're dealing with 30 amps of return current. This is essentially being able to take stray RF off of a cabinet and sending it to ground. So, I mean, it's usually going to be a fairly small amount of current. If it's lightning, that's a totally different story. But in this case, what we're trying to do is if we have here, so let's say we have our transceiver here and we have an antenna and we have some wires hooked up to this transceiver, right? This goes to your microphone and this goes to an external speaker and this goes to a computer, right? Every one of those wires can function as what?
An antenna.
Antenna. Okay. So I'm transmitting a signal out here and inside my station, I've got radio frequency fields, right? I'm sitting in the RF field. So essentially, what are the computer and the microphone and the speaker all attached to? They're attached to the case, right? Everything is grounded. There's always a return path. The case is typically made of metal. And so I have conducted RF energy now because these things are acting as antennas that can actually collect radio frequency energy and bring them back to our piece of equipment, right? But now our piece of equipment, we're not talking about the internals. What are we talking about? We're talking about the metal box around the piece of equipment, right? That's the frame of the radio. So let's say that we have the frequency that we're transmitting on is 30 megahertz, not a ham band, but we're just going to go with that. All right. So what would my wavelength be? So I would get a wavelength of 10 meters,
10 meters.
right? So that would be about 33 feet. Okay. So how long is a quarter wave approximately?
19
About
feet.
8.
About 8 feet. Okay.
8
So
feet.
if I have a cable here that's, let's say, 22 feet to go outside, and I start drawing my wave on this because I know that the wavelength is 10 meters. Okay, well, I'm going to do this. I'm going to start drawing a sine wave. Well, guess what? Am I necessarily at 0 volts here?
No.
No, because this, unlike the antenna that we drew, where your current has to be 0 at the end point, what do we know about ground? What is ground defined as? How many volts? 0 volts,
0
right?
volts.
So this is not at 0 volts necessarily. So this will be at, because this will now attempt to pick up all of the energy that's sitting on the frame of the radio and send it to ground. Well, this works great for AC power, because the wavelength of power is like 3,000 miles long. So that's not a problem. But if we're talking about RF and like on 10 meters, well, one full wave would be 33 feet. So we're at 22 feet here. So we are not at 0 volts right here, which is why if we want to avoid, for instance, what's the risk in this? Anybody know? So let's say this is at 30 volts.
Electric.
Yeah,
Can you
and
get top of the
actually,
antenna?
well, it's not going to hurt you per se, but for instance, I know, like, for instance, this microphone, this was my first experience with it. I had a Kenwood MC50 microphone, which was all metal, and I would key up the radio and I'd lean over to talk into it, and my lip touched the microphone and I got a shock.
Oh my.
It wasn't a painful one, but it was, it was definitely a shock. It was, and yeah, zap. I'm like, oh, what was that? And that was because I had everything grounded, but I was like 60 feet from ground. Well, safety ground, your AC power ground, is very different from RF ground because of the wavelengths that we're working with. So that just basically meant that if at a given frequency, if I change the length of my ground wire, that would change the voltage at which my whole station was sitting when I was transmitting.
So would the effect could also be similar to RF burn if,
Pretty much, yeah, because it's at that frequency. I mean, it wasn't as bad because it was induced. It was induced energy being brought back down through the wires. It wasn't nearly as bad as going up and touching a wire. That
it
was
wouldn't be,
an antenna wire, but
so it wouldn't be,
but I could tell. I mean, I felt it.
so you're basically, like you said, a shock. You're just basically clearing that energy. It's not like a constant, feed, is it?
Oh yeah.
It is.
I mean, but it's probably like microwatts. But
Yeah,
What was your
it's
fix
there.
for that?
Longer,
I-
right? Longer?
Well, number one, I backed off of the microphone and stayed backed off of the microphone. And it wasn't doing any other damage, but I changed the length of my grounding cable. I shortened it a little bit.
Oh, shortened it. Okay.
Yep.
And then would that cause radio frequency interference from the outside of the case back into the electronics or not? Like,
Well, it didn't really, but I mean, yes, it can.
yeah.
And the other thing is that what we'll find, we're talking about when we're talking about induced radio frequency energy, the fact that anything that's a piece of wire can act as an antenna. So let me ask this quick question. Let's say you have a transmitter right here with an antenna that's transmitting signals in all directions. And then your parents happen to have a hi-fi stereo with speakers with 30 feet of wire running to each one. All right. So when you transmit, what do you think happens?
They're gonna go to the speakers,
Well, you won't do any damage to them.
but you can hear it.
You can definitely hear it. Yes. And in fact, you can even hear it with the stereo turned off. So when I was transmitting, my parents would go, they could tell when I was on because I was coming through the speakers. So what would be a potential fix for that?
Go to a smaller wavelength.
Yeah, but you're not going to do that.
They're going to tell you
That
to,
choke.
Better
Yep,
rate
put
choke.
ferrite chokes.
or they're going to tell you to just move everything out into the shed.
Correct. Well, we lived in a townhouse, so that wasn't going to happen. So,
Right.
but you could put ferrites on everything. And in fact, we have a station, the station at the museum at certain frequencies we actually do get into the PA system in the planetarium. And we've tried lots and lots of chokes, and on certain frequencies, it doesn't work. So we just have an agreement where we're not going to operate on those frequencies.
So is it worse on 4 ohm speakers or 8 ohm?
I don't think it really matters.
With the ferrite choke, did you have to splice into the cable, or did they just go over the insulation, or how does that work?
Yeah, well, there's a couple of ways to do it. There's ideally what you have is a ferrite that's big, fairly good size diameter, that you can actually go like this around several times. You get a multiplicative factor when you're able to wrap it several times. If it's a clip-on, you basically can just go, one time through. Sometimes you can go a couple of times through, but ideally what you have is something that's like a really big donut where you can take your cable and wrap it around multiple times.
So you're saying like you can't get rid of certain frequencies. Does that mean you just need bigger ferrites, or are some frequencies way harder to dissipate?
Well, it's not that it's harder to dissipate. It's just it's installation specific. So, I mean, it might be that if we'd actually gone back to the PA system and said, okay, 30 meters is getting into the PA system, we've got to do something. Every other band that we've tried is good, but that one's not. The ferrites seem to be helping on the other bands, but not really on that one. It could be that it's just, there's some amplifier in there that's really sensitive to the existence of that frequency, that we would have to take like, 7 ferrites and wrap the cable through each one 10 times to do it, which means we would be using, 30 feet of microphone cable to get through it, for instance.
It just becomes impractical to deal with.
Right. Exactly. Okay, let's see. We're on the bottom of 56. The source of a high-pitched whine that varies with engine speed is alternator noise. We kind of talked about that a little bit. When you hook up a return connection of a transceiver's power supply, when you're in your car, you would either go to the engine block or to the battery negative terminal. So why would you never, if you can avoid it, why would you never want to use the auxiliary power outlet, which used to be called a cigarette lighter?
It might not have enough power, allow enough power through it.
Yeah, typically that's only good for about 5 amps, depending on the car that you're in.
And if you're trying to bring up the amp on that part, you're definitely going to burn that cable.
Correct. Well, you're probably going to blow the fuse that's protecting it.
Mhm.
Let's see. To remove power line noise or ignition noise, you use something called a noise blanker. The noise blanker again reduces the gain of a receiver when the pulse happens. Okay, we're on to 57. Okay, tuning, filters, squelch, AGC, repeater offset, memory. All right, so we're getting into what your radio actually does and how it works. So if you set your microphone gain too high, that would be the equivalent of me yelling into this microphone. Essentially, whenever you yell too loud, you get distorted. You cause your radio to over deviate. Your microphone basically pushes the radio transmitter circuit too hard. All right, so now what I'm going to do is hide this, and we're going to once again share. If I didn't close it, which I hope I didn't. Oh, I did. WebSDR. We're gonna go to
It's
gonna
I
go
have a
to
question.
yeah.
When the subject that we were talking before about connecting the radio in the car, would it be best using the same battery in the car or using a converter and turning that to DC? Using
I would, well, when you say a converter, like,
there's a converter you can connect to the battery and then you could use like a 110 outlet out of it.
I would definitely not do that. Those are pretty inefficient. I would just use, I would just use 12. If you've already got 12 volts, I would just use the 12 volts.
Okay.
Okay, so So what we have here, can everybody hear?
Yeah.
Okay. So what we have is a digital version of a radio. This is called Web SDR. This is actually in the Netherlands, this particular one. So notice we have a frequency control right here. This is our frequency. This is essentially the wavelength and frequency that we're listening on. So picture that picture that you're looking at a wall and there's a bunch of different colors on the wall. You only want to see one particular color. So you would put a filter in front of your eyes so that you could only see one particular filter. Essentially, that's what we're doing here. A radio receiver is something that functions by listening to one particular color of light, if you want to think of it that way. It just so happens that it's a radio frequency, but that's what we're doing. So in order to change that, we have a keypad or VFO knob. So I can change this to 14030. I've changed my frequency. A VFO is a variable frequency oscillator. Essentially, by being able to change the frequency, that allows me to change what we're listening to. A lot of older radios were known as something called rock bound, which basically a rock is another word for a crystal. So you could operate on one frequency. That was it. You might have 3 different crystals. So then you could have 3 different frequencies, but that was not a variable frequency oscillator, which is why the term VFO exists, because we can vary this. We can tune up and we can tune down. All right. Okay. So very often there's a knob available for doing that. And in order to access a favorite frequency on a transceiver, you can store it in a memory. So I don't have that here, but for instance, on this, this handheld right here that I'm holding right here, this little radio has, I don't know, 200-300 memories in it. And I could, for instance, tell this radio that I want to scan all my memories. And there it goes, scanning memories and listening to whatever it hears and scanning. So anyway, that's a way to store a favorite frequency is just use the memories. If you want to listen to all of your frequencies, you can scan. Again, that's actually one of the questions. The purpose of something called squelch. Okay, this is what squelch activated does. And if I turn the squelch off, I get that. Now, if you don't happen to like listening to that all day,
Not
turn the
hearing
squelch
it.
on. You didn't hear that on my headphones?
No.
Oh. Okay. Let me change it. Okay. How about this?
Now you can hear it.
All right. So squelch off or squelch on. Squelch off. Most people prefer to listen to that when there's no signal there. So that essentially the receiver is turned off or shut or quieted when there's no signal to listen to. Okay, so if the squelch is too low, the radio sounds noisy. The other thing is that if you happen to be scanning, anytime there's a signal loud enough to break the squelch, it will stop the scanning from happening and it will turn the receiver on. So if you're attempting to listen to, you want to listen to active stations, if the squelch is then too low and there's a little bit of noise on one particular frequency, it'll stop scanning and you'll just hear a bunch of noise. So, okay, offset frequency. We're going to do offset frequency. Okay, which means we have to cover how a duplex system works, which means we have to talk about how a repeater works. So here's a mountaintop. Here's a repeater on top of the mountain.
I think you're off your mic. I think you're using your camera mic.
I have to switch it back. I temporarily changed it. There we go. That's better. I assume that's better, right?
Yep.
Yes.
Okay,
Yeah.
good. All right. So let's say that you are down here with a handheld radio And repeater is up here, and there's another person down here with a handheld radio. All right, so this repeater has a published frequency. Let's say I'm going to use an actual example of the repeater I'm the trustee for, of 146.72 megahertz. All right, so that's the published frequency. So what band would that be on? If we look at our frequency spectrum chart, what band is that on?
2 meter.
That is 2 meters. Okay, so if we're on that particular band, the repeater has a published frequency of 146.72. That means that when it transmits signals out to the world, those signals are being transmitted on 146.72 megahertz. So anyone who wants to hear that repeater would tune to 146.72. That includes me and my friend down here. So we are both tuned on our radios to 146.72.
That's
Okay.
the output. That's
That-
the output frequency of the
That is the
repeater.
output of the frequency. That is the output frequency of the repeater. That is the frequency the repeater transmits on at all times. Now, if I was standing on top of a mountaintop, let's just picture me standing on a mountaintop, and this repeater was replaced by me, and I was relaying signals from the person on the left to the person on the right. I would listen to the person on the right. They'd yell really loud, and I'd hear something, and then I'd wait, and then I'd repeat it to the person on the right. And then the person on the right would yell something back up to me, and I'd wait to finish hearing it, and then I'd yell it to the person on the left. Right? That would work fine, correct? I mean, that's a repeater.
Yes.
Okay, that would work fine. The only problem with that, of course, is that you now have a time delay, because you had to wait for one person to finish talking before you were able to repeat the message. And that would be known as simplex, where you're basically on the same exact frequency. You're listening, then you're recording it, then you're sending it out again. It's not possible for everybody to hear what's being said when it's being said. You'd have to wait for it to finish. So what a repeater does is that it listens on a different frequency and simultaneously retransmits what it's hearing. And the key is that it's simultaneous. So the repeater is always listening on a different frequency, which I'm going to use in red, from all directions, because it's not specific as to where it's listening for. It's always listening on a different frequency. So in order for me, the person right here, to be using the repeater and transmitting something that the repeater is listening to, I have to be transmitting on a different frequency so that the repeater can be hearing it and simultaneously retransmitting it. In this particular case, this frequency is 146.12 megahertz. That is my transmitting frequency. The repeater would be listening on 146.12 megahertz and simultaneously retransmitting everything that it's hearing and moving it somewhere else. So when I'm done transmitting, my radio will switch back to receive mode. And let's say another person wants to transmit, they will then transmit on 146.12 megahertz. The same way that I was doing. And because of that, this differential up here, right here,
Is that the deviation?
that's the repeater offset.
Repeater offset.
That's the repeater offset. And by convention, we now say, okay, well, the difference between the transmitted frequency and the received frequency is defined by the distance, by the difference in the frequencies and the direction. So we would then say that this repeater offset is a negative 600 kilohertz, because in order to access it, you would have to transmit 600 kilohertz lower than the published frequency. The published frequency is this 146.72 because that's the repeater's transmit frequency. That's basically saying that your repeater offset is the differential and the direction that you have to be off frequency in order to be heard.
Well,
That's
what
re-
about the positive 600? Like when can you select that to go to, like, say, to 147.22?
So by convention, the break point, if I were to draw the frequencies, it goes from 144 to 148. The break point is at 147.
Oh, I didn't know that.
So usually by convention, these are positive offsets and anything below is negative.
Okay, and I don't know if in the United States that all the repeaters employ what we call tone settings as well.
Most of them do.
You want to get into that?
Yep, we're going to.
Figured you were. Sorry.
Yep.
Okay.
Yeah, that's actually in a little bit. Okay, so we're gonna go.
Todd,
Yeah,
some of the ham operators that we've been listening to talk about doing simplex,
yeah. Simplex is
talking
just,
radio to radio.
right. It's just using the same frequency for both.
And so, and they talk like every ham operator should know how to do that.
That's true.
I'm not quite following what you're about, but
Wait, ask the question again.
okay. So they're saying that every ham radio operator should know how to talk simplex, which is
I agree.
radio to radio. Is
Yep.
that correct? And they usually give a frequency, and they'll do like a little test
Yep.
run, I guess, or
We do it on
Um,
147.42 every week.
okay.
And that's because you have,
you're just setting radio to that frequency, and you're both talking and receiving on the same frequency.
you are. And the reason that you are is because if I have all these different points, there might be terrain in between. And the ARRL is the American Radio Relay League. The definition of the name of the American Radio Relay League is from the word relay. So the reason that we become sort of spoiled using repeaters, because repeaters are usually in a high spot where a lot of people can see them. But there are some times that your repeater is not going to be available, in which case everyone will be on the same frequency. And this person, if they want to get a message out, will transmit the message. And let's say that only this one can hear it. Okay, so you transfer the message to here. This person happens to be in a little bit better spot. So this person might be able to be heard by this person and this person and this person. But you want the information to get all the way up here to the person in the green dot. Okay, so basically now the message now has gotten to this point, and this person might have access to all of these areas. So basically your message has now gone from here to here to here and up to here. And practicing those and knowing how that works, that is basically operating a simplex net, getting information from point to point without the use of a repeater. And we do that every week here in Eugene, because it's good practice. It's good to know what your local terrain is, because we have a lot of terrain in Oregon. You know, there's a lot of hills.
So is each person repeating the message by voice, or is their radio just extending, or you're like relaying from one radio to another radio?
You are the operator. I mean, it's your job. And very often there's somebody who's a net control operator, who is somebody in a better spot, who will ask if there's any information to get from point to point, and that person will direct the traffic. That person will
Okay.
direct the traffic flow, and people will do what they have to do to get information from place to place.
Okay.
Mhm. Okay, let's see.
All right. Thank you.
All right, here we go. So now we're going to go back to our SDR. All right. so receiver incremental tuning. I'll go to a not so busy frequency here. Okay, so notice that we're listening to a given frequency here. We can tune it in. I can change the filtering. There's something called receiver incremental tuning. So let's say I'm trying to talk to this particular station. My transmitter and receiver are combined in one box called a transceiver. Usually these two devices are linked together so that if I change one frequency, I change the other frequency also. So let us say that for some reason, the person on the other end of the string is slightly different with regard to receive and transmit frequencies. So that if I move to make it sound better, let's say I move my dial to make it sound better to me, what will happen is that I will actually change both frequencies at the same time, receive and transmit. So if the other person is listening, they'll say, well, that doesn't sound right. And they'll move their station. They'll move their frequency a little bit. And I'll be right back where I started listening to something that I don't like. So then I'll move again. And then they'll hear something that changed, and then they'll move again, and so on and so on. So there's something called receiver incremental tuning, or RIT, or a clarifier, which allows you to just change the receive frequency without changing the transmit frequency of the radio. So again, that's called RIT, or clarifier. There's another function that we have called automatic gain control. This is a good example of automatic gain control. Here we go. We'll get a nice loud one. That one's really loud and much louder than everything else around it. So the purpose of AGC is to keep you from blowing your eardrums out when you're listening on headphones. Notice this one is much louder than all the others.
What makes it so much louder is just they have a better signal, better equipment.
Signal, closer to the receiver antenna. It could be running more power. But notice that when it first comes in, you can actually hear a little bit of a chirp. That's the AGC circuit kicking in on this receiver. And what it's doing is while that station is present, it reduces the gain of the receiver so that you don't blow your eardrums out listening to it. So that's automatic gain control. The goal is to keep received audio level relatively constant and keep you from damaging your eardrums.
AGC and RIT is digital?
Typically, I mean, RIT is just basically changing one frequency without the other one. AGC can be done digitally, but it's usually not. It's usually an analog circuit, but there's no reason it can't be done digitally too.
Okay.
All right, having multiple bandwidth choices. Okay, so what we're going to do is listen here again. We're going to pick a narrower filter. Why would we want to pick a narrow filter?
Tune it in.
Tune it in, and more importantly, to knock out all the other stuff that we don't want to listen to. So let's make this nice and wide.
Scott.
Yeah.
Can we take 5?
I'm actually in just in two lines. Yes.
Okay.
Yeah. So notice nice wide filter. Notice we're getting swamped by lots of other things. Well, I want that one signal there. I want to listen to that one. Let's see if I can get it. So now I don't have to listen to all that other adjacent noise.
Is that noise data or CW?
It's Morse code.
Yeah.
Now I could also listen to data. This is all data.
Is there a way to zoom in on the frequency so you can get even more acute on that?
Sure. That's as close as I can go on this one.
Oh, I see. Okay.
That's actually like 7 or 8 data streams right there.
Wow.
Multiple stations operating at the same on the same band. But now I don't know if we're going to hear anything, but let's go to the voice band. You might hear somebody.
Yeah.
Can you be like Snoopy and start decoding what they're sending and listen in?
Well, actually, I will get to that in a second. All right, so this is an appropriate. This is about 3 kilohertz, 3,000 hertz. That's a nice, comfortable bandwidth for voice. I think we'll find. Okay, so that's. This is about as narrow as you'd want to go for voice, about 2.4 kilohertz. For Morse code, you want something 500 hertz or narrower. Now, to answer the question that you were asking, we are not allowed to encrypt or hide the message of anything. So basically, if you use a secret, even if you're speaking English, but it's a secret code or something, that's actually illegal. Whatever you're saying.
I thought you could send some things to the space station that way.
Yeah. You can send control, you can send signals to and we would get to that. We're going to get to that. But we're going to basically the only times you're allowed to encrypt anything is if you're sending signals up to a space station, so a satellite that you have orbiting, for instance, or a balloon above 30 miles up.
Okay.
Or if you have a remote control craft, like let's say you have a long distance remote control and you're doing like an RC boat or an RC plane or something like that.
Yeah.
The
Okay.
only times you're allowed to encrypt anything.
Okay.
But even speaking, in like plain English, but using codes is not legal.
Mm-hmm.
The data stream that you were listening in on, can you like
Anybody has to be able to get access to the decoding mechanism.
Okay, so if you start downloading whatever they're sending, it could be like a cooking recipe or something.
Yeah.
Something simple.
Yep.
Okay.
So I mean, literally, you're allowed to use new protocols so long as you make the encoding and decoding algorithm available to everyone.
Okay. And how do you do that at the beginning of your transmission or throughout
No,
it?
you usually publish it.
Okay.
So literally, like, WSJTX, the FT8 protocol, they basically said, okay, we're going to use this. Here it is.
Mhm.
So you can't, there's nothing secret.
Okay.
And PTT, does everyone remember what PTT is?
Push to talk.
Push to talk. That would be, in simplest form, the button on the side of this radio. All right, everybody ready for a 5-minute break?
Yeah.
Okay.
I got a silly question.
Okay.
When you hear somebody's voice and it sounds like they've been swallowing helium, what are you getting?
So what I will do is I will share this, and I call it Donald ducking somebody. Like this. Like that.
Yeah.
That's an incorrectly tuned single sideband signal. Because
Okay.
remember when we did single sideband, one of the things about single sideband is that when I draw amplitude modulation, frequency spectrum of AM, it looks like this.
Okay.
And this is the carrier. And I have an upper sideband and a lower sideband, right? Well, the carrier provides a reference point for your receiver.
Yeah.
Well, in single sideband, we get rid of the carrier and we get rid of one of the sidebands. So basically, you are responsible for picking the reference point. So if you picked it right here, everything that was here would suddenly be too high. If you pick a frequency with a carrier frequency there, then stuff that's here would be down below. And stuff that here would be too low. So essentially that shifts the that does an offset of what you're listening to.
Okay. Thank you.
Yep. All right, break time.
Looks like somebody else is a flashcard person.
I've gone through about 700 of these silly things.
I know. I bought them and I go through them occasionally, decide
they-
which ones I know and which ones I don't.
Yeah, that's what I'm doing. I'm separating out what I'm missing.
All right, everybody. Questions?
So like, let's say you wanted to tune into a specific repeater. You need
Yep.
to program your radio to transmit on a certain frequency and receive on whatever that receiver's or that repeater's transmit frequency would be.
Yeah, so here, let's go to repeater book. Just for the heck of it. Here we go. We'll go to repeater book. And it used to be that you used to have to buy a book to go online or to get information about repeaters. Now this is made public, which is a great thing. We'll go to, we'll look up repeater book, W7PXL. Okay, this is the repeater I'm the trustee for. One repeater found. There it is. Okay, so right here, frequency 146.72 with an offset of negative 0.6 megahertz, which is the same as negative 600 kilohertz. So it tells you what the offset distance is. It's negative. So basically you would have to be transmitting on 146.12. And notice this tone uplink and downlink. That's the CTCSS or PL tone that we started to talk about a little bit. Essentially, this is a subaudible tone. That is because it's subaudible. It's basically a low hum sounding thing. It's usually stripped out of the audio before you even listen to it. But basically, there are 38 different CTCSS or PL tones that can be transmitted. And essentially, it's like a key to the repeater. So if you're not transmitting with the proper tone, the repeater will not open its receiver for you, and it won't retransmit you. Don't want to.
Hey, so I got a question. So I've got an old Kenwood radio that somebody lent me until I get a proper one, and I'm not receiving because I'm not licensed. Listening into the repeater. So when it comes time to transmit, I won't be able to transmit with this radio because it doesn't have tone settings.
Correct. Unless
Wow.
you have, yep.
So you can get an external toner, is what you're going to say?
It's,
No.
I mean, it's possible, but usually it's not an easy thing.
Oh, so this radio is basically useless unless I'm going to be simplex talking to someone.
Or, I mean, you can certainly listen to it.
Right. But
Yeah.
But you can't even use it in the field or like for
Oh,
simplex.
sure. Why not? But
I don't
mean,
know. Is it practical to even keep it or use it for that kind of purpose?
how old is it?
Oh man, it's like TR 7400, like the 70s.
Yeah, I mean, it's a receiver. You can certainly use it for that. You can use it for simplex.
Yeah. Okay, that's what I was thinking. But I mean, that's
about it.
Yeah, it's basically gone by way of the dinosaur or whatever. So I see what you're saying. Okay, so that answers that. Wow. So yeah, so there's the reason for these tone things. They brought in just a quick. I guess I was told, well, the interference with like cellulars and everything else.
No,
It's not the reason.
no.
Uh,
The reason that this happened was, you can look to Southern California. So what we're going to do is draw the Los Angeles basin. All right, here's the LA basin. Essentially, LA is a huge population ringed by mountains, right? And so you have all these people in this basin wanting to use the radio. And there are only so many frequencies available. So what Motorola did was they came up with this system called PL, which is private line, where you could have all these different systems operating on the exact same frequency, but this would have like a 67.0 tone. This would have an 88.5. This would have 100.0. This would be 123.0, and so on and so forth.
and those
So-
are Those are
Those are
repeaters.
all repeaters, but they're on the same frequency. So let me ask this question. If I'm down here and there are two transmitters transmitting at the same time from these repeater stations, what am I going to hear? On
Feedback.
FM, on FM. What am I going to
Nothing.
hear? I'm going to hear nothing. The reason I'm going to hear nothing is because that's the way that FM works. FM has to deal with something called the capture effect. And if you have multiple signals on the same band, which is if you've ever listened to a repeater and a couple of people using it, you hear something called a double. When two people use it at the same time and they basically obliterate each other.
Mhm.
The reason that is because FM receivers favor the stronger signal. And if there are two signals that are about equal strength, you hear neither one.
Yeah.
So the way that this now works is that only one of these repeaters can be used at any given time. But what it did allow people to do was to say, like, let's say that these were not selective and I just transmitted on an offset frequency. All of those repeaters would be activated, right? So now the way this was set up was I selected a transmit PL tone of 67.0. That would light up only that repeater.
Mm.
So that was Motorola's way of being able to reuse frequencies. And this has permeated all the way through, you know, all these little FRS radios, 38 channel FRS and GMRS radios. And the problem still is that if there are two different transmitters transmitting on the same frequency, you still won't hear anything, even if they have different PL tones. But at least it quiets things down. It allows people to use multiple different repeaters in the same area.
And also, I guess, like in this area, for example, obviously not like as thickly populated as San Diego, but we have a few repeaters that are like, 50, 100 miles in near talk apart as crow flies, and they're linked for transmitting. Does that sound right? They
Yeah.
link.
They're just linked. Yeah, it's a link system.
So any traffic on any repeater gets broadcasted to the one you're tuned into.
Actually, any traffic on any repeater gets sent to all of them.
Okay.
And we actually have a system out here in Western Oregon where we have 50 repeaters all connected all
Right.
around the state.
So how does that in the end really help with the like traffic not being congested?
Well, it is congested.
It is.
Yeah, people have to view it as a resource, and you have to know that you're not going to get on there just for idle chit chat.
Right. Okay, yeah. But at least you can differentiate the signals. They're not all garbled that way. Okay. Right?
Right.
So my next quick question is, how dependent is this system on digital and the web and all that?
Not a lot. It's mostly microwave links for the backbone.
And I meant for the toning too.
Oh, not at all. I mean, tone is just an analog tone.
Okay, man, that's good to know. Well, I thought it was like if something happened, like everything would go down, but.
Well, I mean, there are ways to link repeaters together using the internet. I mean, it's something called Echo Link. There's another one called All-Star.
Yeah, but they're independent, like totally from what we're talking about. Yeah.
Well, those are internet linked.
Yeah, but they're independent of the, like you just explained, the analog system of the repeaters themselves.
Yeah. And even if it's a digital repeater is still just a repeater unless it's linked to something else using the internet. So.
Oh, I see.
Yeah. Just digital. It's just, digital DMR or Fusion, Yaesu Fusion.
Firmware.
Yeah, essentially.
Yeah.
Okay, here we go. We're on to page 60. What is a transceiver? A transceiver is a combination of the word transmitter and receiver. A transverter, That's a device that shifts frequencies from one to another. So for instance, a transverter would be something that goes like this. Let's say 28 megahertz in, goes through this magic box, and the output would be 222 megahertz, which is the 1.25 centimeter band, or sorry, 1.25 meter band. So this actually, we're going to get to this. We might as well do it right now. So this is actually a device called a mixer. If it's bidirectional, this would be like an entire box. This would be a transverter. It's a transmitter converter. And the core of a transverter is a device called a mixer. A mixer is a very special kind of device which provides it's a nonlinear device, so it's not like an amplifier. What it does is it takes a frequency A and a frequency B, and it produces A plus B, and A minus B, and B minus A, and A plus 2B, and 2A, and 2B, and lots and lots and lots of other things. So the most simple one that we're going to do is A plus B. So in this case, 28 plus something is 222. That would be 194 megahertz. So this mixer, which is the heart of this transverter, would have this oscillator generating a frequency at 194 megahertz, which would then be added to 28 to give us an output of 222. But now notice that I did say that all these other noisy things are made, right? A minus B, B minus A, and so on and so forth. How do you think you eliminate those? If I were to put this on a graph, I would see at frequency 0 to infinity, I would see 28 and 194 and 222. I'd see those, and then I'd also see this, and maybe this, and this, and this, and this, and this, and a whole bunch of other ones. This is the only one I want. What would I do to do that?
Filter.
That would be a filter. I would make a filter that would pass just that range of frequencies that I wanted and block all the other ones. And we're going to get to filters very, very soon. Okay, what device increases the low power output from a handheld transceiver or any transmitter for that matter? That would be known as an RF power amplifier. So this is another interesting thing about transistors. Okay, so I'm going to draw a transistor right here. You guys remember if that's a PNP or an NPN?
NPN.
NPN, because it's not pointing in. See, nice and easy to remember. All right, so if I were to draw the curve for this transistor where I have an input and an output, what do we know about if this is completely off? Does it work at all? It does not.
No.
We have to have at least something before the transistor actually even turns on. So we get up to a certain point where we have no output. But then it starts to come up. And it eventually comes on and it looks like this. And then it gets to the point where no matter how much more signal you put in, you can't put any more out. You've maxed it out.
Saturation.
Right? So this is called cutoff. And up here is called saturation. But in between, what do you notice that this nice little shape is? What does that look like?
Linear.
Mhm.
Sine
That is a
wave.
line. That is the linear region
Hmm.
because it looks like a line where something that you put in will produce, once you
Gain.
take away the offset, will produce a linear response. So if you make something 3 times bigger in this range, it'll produce something 3 times bigger on the output. So this is known as the linear region of a transistor. And when we do this, the reason for doing this is because some signals that we want to produce, such as voice, if it's not linear, if it's not multiplied in a linear fashion, it sounds all distorted. So single sideband requires a linear amplifier. So for those of you who have seen something called a linear amplifier, that is why we have something called a linear amplifier. It operates in this linear range. For other things, we don't really care if it's linear so much. FM, an FM signal looks like a rectangle. We don't really care whether that's a perfect rectangle or not, because when it gets to the receiver puts it through a limiter and chops off the top anyway. And because we're just looking at a bunch of frequencies that are dancing around inside this rectangle, it doesn't really matter what's happening above that cutoff line that the receiver does. So what ends up happening is for an FM amplifier, we can actually operate in a much bigger area of this range. We're just looking to see whether it's on or off. So what that means is, because if there's no signal at all, if we're not doing anything, we basically want to aim for the center of the range so that when we go plus and minus, we can actually see something linear. For FM, we don't really care. And that's why a lot of power amplifiers have a switch that says FM SSB, because what it does is for FM, for instance, it will make the central point right here, which means that you're not using nearly as much power to generate your signal when there's nothing there. So the efficiency of an FM amplifier is typically much higher than the efficiency of a sideband amplifier. And that's why a lot of amplifiers will have a switch that says FM/SSB. It changes the operating mode of the amplifier, typically from a class A or class AB to a class C. But that's for a later date. What term describes the ability of a receiver to detect the presence of a signal? That is known as sensitivity. And selectivity is the ability of a receiver to discriminate between multiple frequencies. And what we can do is, once again, we can go to our web SDR for this. And this is just a great tool to have. Okay, so let's find a nice quiet signal in here. All right, that one's not too loud. Notice some of them are louder than others. Basically, sensitivity is the ability to hear the quietest thing that you can hear. That is what sensitivity is. If something pops up as being present. Selectivity is the ability to do this.
Yeah, that's so. I got it on her nose. It's like stuck on her nose.
Hey, Scott, what is this webpage we're looking at coming from Twente, Netherlands? That's where my son lives.
Oh, this is University of Twente.
Okay.
They have a web SDR at their site at school.
All right.
So basically what we're doing is looking at the ability of this thing to be a selective receiver. So through the magic of digital signal processing, we're able to demonstrate what a selective receiver is. The ability to reject a whole bunch of things while listening to just what you want to hear.
Scott, real quick,
Yeah.
Going back to amplifiers.
Yeah.
Does the amplifier increase only the transmission, or does it also increase the receive signal?
It depends. If it's a power amplifier, it only does that. If it has a receive preamplifier, then it does that too. Depends what you do.
Okay.
Okay, well, here's that question. Where is an RF preamplifier installed? So let's ask this question. So here's our XCVR. This is transceiver. And here's our antenna. This actually is a very good point. All right, so the question is, where does a receive preamplifier go? And what is the function of a receive preamplifier, everybody?
They'll amplify the signal coming in.
Amplifies the signal coming down. That's right. Okay, so we're going to draw this in a way that will be interesting. We'll say that our receiver minimum signal is minus 120 dBm. And our antenna, if we were to measure the signal right here, the signal is minus 118 dBm. Our receive preamplifier is basically a receiver, and it has a minimum discernible signal of negative 120 dBm. All right, so we're going to look at this and say, does this system work? This amplifier has a gain of plus, let's say, 5 dB. Pretty small amplifier. Okay, so if we were to put this preamplifier all the way up at the antenna, so essentially this is 0 length. This is right up at the antenna. What would the input signal from the antenna be at that point? Be negative 118 dBm, which is slightly higher than that. And then we add 5 decibels. So that becomes minus 113 dBm. Okay, so now we have a cable that has a loss of minus 5 dB. So what's our signal right here at the transceiver?
We're back at minus 118.
Minus 118. Does our system work? It does, because the signal is bigger than it has to be. So now what we're going to do is change this length. And we're going to say that we're going to have 50 feet of cable up here. And we're going to have the cable now has a loss of minus 5 dBm. And we're going to make it really convenient. We're going to have our preamplifier down in our station right next to the transceiver, because we don't want to have it outside in the weather and et cetera, et cetera. So now here's our station. There's our station. All right, so what is our signal right here where it enters the station? We have minus 118 and then minus 5. We have minus
123.
And what did we determine that our preamplifier is good for?
Plus 5.
Well, but it needs to have a signal of at least minus 120. So this system has gone from working to now the signal's not even loud enough. There's not even enough signal there to amplify. So sure, we can do a 5 dB amplification. What are we amplifying?
Nothing.
Amplifying noise. That's it, right? So we have no usable signal at that point. So the location of a preamplifier is actually very important, which is why if you're doing a station where you have very, very weak signals like moon bounce or something like that, it's very important to have your preamplifier out as close to the antenna as possible, because you can't amplify what you can't hear.
That was all because the preamplifier required it no worse than negative 120 dB, right?
That's right. But that's going to be something that, amplifiers have noise figures, and they have like a minimum discernible signal. Basically, at some point, you can't amplify what isn't there. Okay, let's see. We already covered this one. A device used to convert a radio signal from one frequency to another. It's at the heart of a transverter. That's known as a mixer. And so if we were to take this circuit right here, what do we call this thing again?
Transistor.
That's a transistor. Okay, if we were to take this transistor and instead of sending out the signal that that we were making to an antenna, if we were to take some of that instead and do this with it, whoop, what do you think would happen if we took some of our signal
Feedback.
and we sent it back into the transistor? That would be feedback. That would be feedback. Well, if we have
Oscillator.
feedback, then basically we would generate at whatever frequency this was coming out as, that would be what we would put back in. And that would cause it to make signal going out, which would make it more signal going back in, and it would go around and around and around, and this is called an oscillator. And you've probably heard of something like this. If you've ever been somewhere where there was a PA system and somebody got too much of the audio from the speaker back into the microphone and it went.
Yes.
That is unintentional feedback. Sometimes, however, we do this feedback on purpose in order to make an oscillator. And that's to basically generate a frequency at a frequency that we want to generate. So we might have a frequency that we need to generate of 194 megahertz so that we can build our transverter. And what we would do is actually we'd add some capacitors and inductors and things like that into this circuit so that our actual oscillating frequency, our actual operating frequency is 194 megahertz. And you'll remember that capacitors and inductors have this nasty habit of having ZL of 2 pi FL and ZC of -1 over 2 pi FC. Well, the interesting thing about that is that there's that frequency thing again. If we pick our L and we pick our C, so we pick our capacitors and inductors, we can actually specify a point where these cancel out and we have something called resonance. And that resonance is the frequency where that happens. So if we were to pick 194 megahertz, we could generate an oscillator that would oscillate at the desired frequency of 194 megahertz just by picking our components in our circuit. So that is using something that we would normally think of as a problem to our benefit. All right, the process of combining speech with an RF carrier signal is known as modulation. The easiest way to show this is with amplitude modulation. So here's our carrier. It's a very much higher frequency than the modulating frequency. And this would be somebody's voice. So what we do at that point is we end up with something that looks like this. That would be known as amplitude modulation. And this right here around it is known as the envelope. So that's the envelope. And this inside is the carrier frequency. So that is modulation. Modulation is basically the act of taking one signal and modifying another signal with it. And usually we modify a carrier frequency with some kind of information. Now, the important thing to realize is if we were to draw the frequency spectrum and we just have an unmodulated carrier. So let's draw an unmodulated carrier. Unmodulated means it never changes, just a carrier. How many frequencies exist in that? That would be one. That looks like this. We just have a carrier frequency and all of our energy is in that one frequency. As soon as we start to modify it, it does this. As soon as we modify it with information, it takes up space. Information requires bandwidth. If you put information into a signal, it is required to use bandwidth. That is just a fundamental of the mathematics of modulation. Basically, if you put information on a signal, even if that means you are sending out Morse code. What is Morse code? On, and then off, and on again, and off. And there's a little off. Here's an off, on. The fact that it's turning on and off is actually modulation. And believe it or not, even though if you look at it, it only has one frequency, right? It's just being turned on and off. It actually has bandwidth. It will actually have sidebands, even though it's just a single frequency being turned on and off. The act of turning it on and off makes it take up space in the frequency spectrum. It's a little counterintuitive, but it's true. Okay, radio frequency interference. We're on page 62. Which of the following will cause radio frequency interference? Fundamental overload. That basically just means that there's just too loud of a signal nearby. Harmonics. If I have a transmitter that's operating at 10 megahertz, what would a harmonic of that be? We're getting back into music, right?
Yeah.
What's a harmonic of 10?
20 megahertz, 30, 40
20,
megahertz.
30, 40, 50. Yeah, all integer multiples of those.
Yeah.
And then spurious emissions. A spurious emission is a non-harmonically related signal that is somehow coming out of a transmitter. So if I have a transmitter that's at 10 megahertz and it's spitting out a signal at 17.2, I don't really know how it got there. It could be that there's some kind of oscillation going on inside the amplifier that I didn't want, that's being amplified and sent out. That's a spurious emission. So one of the reasons you might ask is, why on earth do we have to know all this stuff? The reason we have to know all this stuff is because what is one of the things we are allowed to do with a ham license? Build your own stuff. There is no other service or hobby or anything within the FCC guidelines that allows you to build your own stuff and put it on the air. Right? We are allowed to build even with a technician license. So don't think that it's just a technician license. You are allowed to build your own stuff and put it on the air. Now, if you're going to build your own stuff and put it on the air, hopefully you know that your fundamental frequency is of a certain level, and that you know that your harmonics and spurious emissions are at least negative 50 decibels down, or depending on where you are, negative 60 decibels down, and are able to figure out what that means, because these are spectral purity requirements, which largely manufacturers have to follow if they're building something like an FRS radio, for instance, that is type accepted, or a business band radio. But what are we allowed to do? Build your own stuff. Well, if you're allowed to build your own stuff, that means that you have to be responsible for knowing the rules and testing out your own stuff before you put it on the air, that says that it has to be at least 50 or 60 dB down, depending on where you are. So you have to know what those rules are and why they exist. And why do those rules exist, everybody?
to keep everything smooth.
Yep. You don't want to be interfering with anybody because you can build your own stuff. You have to make sure that you meet the spectral purity requirements and that you understand those rules enough to go ahead and build it. Even if you never plan to, the fact that you have a license, even a technician license, means that you are allowed to, which means you need to understand.
Standardization.
Yep. Okay, which of the following actions did you take if your neighbor tells you that your station's transmissions are interfering with their radio or TV? The first thing to do is make sure that everything you have is working properly and check your own TV or radio and make sure it doesn't interfere with that. So we are covered by Part 97 of the FCC rules. That is the guidebook to ham radio in the FCC rules. There's another part that's called Part 15. Part 15 covers, for instance, power supplies or the electronics on my headset or the cell phone, for instance. Part 15 is unlicensed and unintentional radiators, things that transmit a signal but are either unlicensed because their power levels are low enough, or they are unintentional but do it anyway. So essentially, like if this power supply, this is a Part 15 device. If it happens to transmit a signal, then so be it. However, what it means is that's an unlicensed service, and as licensees, we are immune from Part 15, which means that if we are interfered with by something that's a Part 15 device, we can actually tell whoever owns it, including ourselves, to turn it off because it's interfering with us, and we, being hams, are a licensed service. Similarly, if we, for instance, are transmitting and it makes somebody's TV go haywire down the street, it is not inherently our responsibility to fix this problem. The TV is a Part 15 device. If we are interfering with it and we are operating within our legal limits, and if we are operating correctly and our equipment is operating correctly, it's really their fault. Now, as a neighbor, it's a good idea to go ahead and try to help them out, but it's not your responsibility to do so. Okay, so the first step, in case there's cable TV interference from your station, make sure that all the connectors, all the TV coaxial connectors, cable box and everything are tight. These have a way of loosening over time, and a loose connection will allow leakage to get out and leakage to get in. So your transmitted signal can sneak in. A broadcast AM or FM radio receives an amateur radio transmission unintentionally. I noticed this when I was once listening to my ham radio driving by a very, very, very powerful AM radio station. And on my ham radio, I received the AM radio station because I couldn't do anything about it. I was right next to it and it was transmitting at 50,000 watts. So even if the power level was at 100th of a watt on the ham band, I was still going to hear it. So that would be inability to reject strong signals. How can overload of a non-amateur radio or TV receiver by a station be reduced or eliminated? All right, so we're talking about filters. Filters, filters, filters. All right, so what we're going to do is draw some filters. Okay, so here's our in, and here's our out. So we have a black box. Okay, so if I were to draw my frequency chart from 0 to infinity, and this is full strength up here, and this is 0, a filter that looked like this, which passed low frequencies and cut off the high frequencies, that would be called a low pass filter. Similarly, if I had something that blocked low frequencies and cut and allowed high frequencies to pass, that would be called a high pass filter, right? Okay, so now, how about if I had a filter that did this, was zeroed out, and then allowed just a certain band of filters to pass?
Band pass filter.
That would be called a bandpass filter. Okay, so anybody know where you will find these three filters in a piece of everyday something that you use?
Radio.
Yeah, and what kind of radio?
I mean, AM radio, FM radio.
AM, FM radio, and in particular, anyone have any three-way speakers in their car?
Yeah.
Okay, well, here you go. This is known as, for audio, this is known as a crossover network. Because what is the point of sending your really low frequencies to your tweeter? Not going to know what to do with it anyway. So what you would do is you send your low frequencies through a low pass filter, send them to your big speaker, your mid range through your band pass filter, to your middle speaker, and your high pass to your tweeter, so that each of these speakers has frequencies that it can work with. So in an audio system, this is known as a crossover network. In radio, what we do is we are able to build filters using capacitors and inductors in different configurations to give us filters that act in certain ways. For instance, if I were to draw a filter that looked like this, this would be our C, this would be our L. This tends to pass high frequencies, and this tends to move low frequencies. So this filter response would be something that would look like this. That would be a high pass filter. If I swap the positions of these things and made it look like this, this would pass low frequencies, and this would move the high frequencies down, and my new filter would look like that. And the point at which these transitions occur is determined by the components that you pick, capacitors and inductors. And what's kind of cool about this is that now we can also take this and we can draw a low pass filter, a high pass filter, and then follow this up with a low pass filter. Actually, let me redraw that. I don't like the way that came out. I'll keep the same basic network design. And by selecting this section, this is a high pass, and this is a low pass, I might have them so that they barely overlap, so that this one looks like that, and this one looks like that. And I get the intersection of the two, and that becomes a bandpass filter. I could also take these and make it so that what I end up with instead looks like this. Any idea what that would be called?
Notch filter.
That is a notch filter. It's kind of an upside down bandpass filter. And that's just by selecting components. So these things are extremely useful. And where you will find things like this, does anybody know what a repeater is? We've heard that before, right? Okay, so 146.72, 146.12. Well, what do you notice about those frequencies? They're actually pretty close, right? Especially if you have a transmitter here and a receiver here, and they are using the same antenna. Because what would happen if there was no filtering in between them? Your transmitter would transmit, and where would a lot of the signal go?
The receiver.
Right into the receiver, which would at best destroy your receiver. That's the best possible outcome. So how do you separate these two frequencies?
With a filter.
Filters, filters, and more filters. And very often what you'll find is that the isolation between the two sides is 100 decibels plus. And remember, 100 decibels is 10 times 10 times 10, 10 times. So of the transmitted signal, 0.000000001 of that transmitted signal can make it back into the receiver. And since it's on a different frequency, 100 or more decibels of isolation actually fairly well protects the receiver. So what's interesting about that is if you actually get into looking into what a repeater, VHF repeater duplexer looks like. I will show you a picture of a repeater duplexer. There's a 2-meter repeater duplexer. That is a capacitive and inductive network. Clearly, this is not small. And notice it's $1,800, right?
Yeah.
This is when you use a 2-meter repeater, you have something like this that is separating the two frequencies out so that they don't interfere with each other.
So on a repeater, you would use filters, not like a mixer or anything like that. That would just be on a transceiver, or
Yep, you just use a filter and then you use a controller to take the received audio and send it to the transmitter. And you would actually have to tune using these stubs up top. You would actually have to tune your cavities. This is actually a hollow cavity.
Why are
Where-
they so expensive?
Because they're aluminum and tightly machined.
Okay.
Why are they so much more than like a 440?
Because, well, think about it. What's the wavelength on 2 meters? Not a trick question.
2 meters.
2 meters. What's the wavelength on 440? 70 centimeters.
70.
They're physically considerably bigger.
Mhm.
If you look at, for instance, a VHF low. If I look up, let's see, a VHF low duplexer. That's, let's see if I can find one at the bottom end. I can't even really find one. No, those are not what I'm looking for. If I try to find a 6-meter duplexer, I can't even find one. This is a VHF bandpass. Basically a 6-meter duplexer, they're taller than you are.
Wow.
Yeah. And that's because they have to have a lot of rejection. There's a lot of decibels of rejection in there.
is it possible to set up just a regular transceiver as a repeater?
I mean, not on the same band, but you can have a crossband repeater where you can run on 2 meters and 440 separately, because those are, far enough apart that they're not going to interfere with each other. Now, repeaters fall into the category of automatic control, and a lot of the transceivers you can buy today, they have crossband repeat functionality, but they don't have what it takes to do it legally in the United States. Which is every amateur station has to do what? Every 10 minutes.
Call sign.
It has to identify itself. That's right, with a call sign.
Isn't the 10-minute thing under 10 minutes, not at the 10 minutes? Because there's a couple of questions that confuses me.
Yeah, it's just every 10 minutes and at the end.
Okay.
So it could be right, it's 10 minutes or less. But the key is that it has to be identified every 10 minutes. Which basically means that the transmitter itself, not the person using it, is supposed to identify the transmitter. So there are a few mobile radios that do crossband repeat that identify using Morse code. You can set them up to ID using Morse code. Many of them do not. And you can build your own IDer to do that, which every 10 minutes will send out a Morse code ID.
What about an Alexa voice?
That would be okay. Yeah, so long as it's automatic. That would be fine. You can use voice to identify a transmitter.
So like listening to repeaters on my handheld, I'm not hearing a repeater identify itself. Is it doing it via Morse and I'm just not?
Yeah,
tuned in?
it's usually IDing over Morse every 10 minutes. If it's not transmitting, it doesn't have to, but when it's operating, it always has to transmit an ID every 10 minutes. That's probably it's probably a CW ID.
So if you're using a repeater, does it cut you out?
No, it superimposes one over the other. So yeah, if
Do
somebody,
you know off the top of your head whether the DR2X has that repeat or that identifier?
I do not.
ASU? Okay.
I know that the Kenwood DR710GA, I know that one does, but you know, that's a $700 mobile rig. So
Yeah, okay.
there aren't many that do. Okay, everybody, what is a Part 15 device? What's Part 15 again?
Unlicensed.
Unlicensed transmitters. So an unlicensed device that can emit low-powered signals on frequencies used by a licensed service. My antenna analyzer is a Part 15 device. It transmits 1 milliwatt or less. I can transmit on any frequency that it can transmit on. It's a Part 15 device. If something in your neighbor's home is causing harmful interference to your station, work with your neighbor to identify the device, inform your neighbor about the rules that prohibit the use of devices that cause interference, and check your station and make sure that it meets the standards of good amateur practice. If you have a report that your audio signal is unintelligible or distorted, your transmitter can be slightly off frequency. You can be in a bad spot. In other words, you don't have a good signal path between you and the repeater, or your batteries can be low and it's not the battery voltage is not enough to keep the transmitter working properly. RF feedback in a transmitter or receiver, basically that would be that your transmitted signal is getting back into your microphone circuit. And then you end up, basically it's bad. And if somebody says that you're all distorted and garbled, that means that basically you have RF getting back into your system. If you're over deviating, deviation is a ratio by which your spoken voice transmits to how wide an FM signal spreads out. So what did we say? What did we say the bandwidth of an FM signal is on voice?
10 to 15 kilohertz.
10 to 15 kilohertz. Most stations on VHF do 10 kilohertz. So plus and minus 5 kilohertz of deviation. If your deviation is too high, what you'll get is that your signal then goes too wide. If it goes too wide, some of the information in that spoken voice that you're sending out will get clipped off. It just disappears off the ends and you end up sounding distorted. So the solution to that with most handhelds is to just back away from the microphone.
Okay, so it wouldn't be like a faulty modulating circuit, like a mixer circuit doing it?
No, it wouldn't be the mod. Basically, there's in an FM transceiver, essentially you end up doing this. I mean, what you end up with an FM transceiver is that you have deviation, and I mean, it's basically a circuit which, depending on the audio that comes in, causes your signal to spread out. And the further that it spreads, like some transceivers, they actually have a deviation control inside. I don't think this one does. But some of the older ones would, you know, they'd have a potentiometer for deviation control. And if you actually take it and put a calibrated signal in, it will spread out a certain amount. And so you could actually make that adjustment. Most of these today are like a transmitter on a single chip. So you get what you get. We're on page 65. Okay, so what we're going to bring up is a picture of a Fluke 87 multimeter, because we're talking about meters and measurement circuits. Okay, so this is a Fluke multimeter. This is what I use at work. Oh, stop it. Okay, so notice the different settings that we have here. We have volts, we have millivolts, we have ohms, we have amps. So this is a multimeter. It's a digital meter, and it displays, again, volts. The squiggle over it would be AC volts.
AC,
The straight
DC.
line would be DC volts. Then we have millivolts. This one also does temperature. It does resistance in ohms. Notice it can do a capacitance measurement. There's a capacitor there. A diode check, AC milliamps and amps, and DC milliamps and amps, and also microamps. So it has different settings, but notice this thing also costs $650. I guess they went up a little bit. Now, what you'll also see on this is, notice what this says down at the bottom. Category 3, 1000 volts. Category 4, 600 volts. So this is actually what I use in industry if I'm suited up properly to measure 480 and 575 volt circuits. Now, I can also go to Harbor Freight. And everyone familiar with Harbor Freight?
Yeah.
Harbor Freight. There we go. I can go and get a Harbor Freight multimeter. I'll bring this up. Notice 4.4 stars, pretty well thought of. The other one was $650. How much is this one?
$7.
$6.99. Okay. And now, if you look at this, you will see that this says 1000 volts DC, 750 volts AC. And it also measures resistance and DC volts, AC volts, up to 750 volts, DC amps, and so on and so forth. Oh, and look, it even has a transistor checker and a diode checker. So what is the difference between this and this?
Accuracy.
Accuracy and what else?
Reliability.
Yeah, reliability, safety. Like, for instance, would I ever use this to measure a 460 volt circuit?
Hell
No.
no.
I don't think so. I mean, just because it says it on the label, I don't think I would.
Do it once.
Yeah, you might be able to do it once, and I hope you're wearing some protective gear when you are.
Arc suit.
Yeah, well, I have an arc flash suit for those
Me
voltages
too.
anyway, but so anyway, they both measure the same things. The most common things to be measured on a voltmeter are volts and ohms, voltage and resistance. To measure electric potential, you use a voltmeter. The way to use a voltmeter is that you put it in parallel with the circuit. So if I have a battery, like here, I would do this with my voltmeter. I put it in parallel with the battery. All right, if I have an ohm meter, so what an ohm meter does is allows you to measure resistance. So I put that in what looks like parallel with my resistor. Now, it's very important to have the resistor disconnected because, again, what is Ohm's law? One more time, everybody.
V is equal to IR.
E is equal to IR. Okay. Now, what do I have here? I have a resistor, right? I have an unknown resistor. And I'm trying to measure it with this meter. Well, okay. Well, if I have a resistor there, what do you think is actually in my meter?
Current source.
Current.
It's got a battery and it's got an ammeter measuring current. So what it does is it puts a voltage, let's say 9 volts, through this, and it says it knows, okay, 9 volts, and it measured, let's say, 9 amps. It would never do that, but Let's say it measured 0.009 amps. So E is equal to I times R. R is equal to E divided by I. It's equal to 9 over 0.009 is 1,000 ohms. So why is it important to never have this circuit powered from a battery when you're testing resistance?
Because it'll affect.
You'll fry
the
your
output.
meter.
Yeah, number one, you'll fry your meter. Number two, the answer that you get might not be correct.
Yeah.
But yeah, you can fry your meter that way too. So that is why it's important to disconnect something that you're testing from a power source. And in fact, sometimes in order to do that, you might actually have to unsolder something so that one leg of the device is not connected to anything.
What's that?
Okay, what do we use to measure resistance? Again, that's an ohm meter. In order to measure circuit resistance with an ohm meter, you have to make sure it's not powered. You can fry your ohm meter. You can fry your multimeter when using the resistance setting if it's connected to something that's already powered. And okay, so let's say we have our ohm meter. And remember what's inside an ohm meter? It's a battery and an ammeter. And I am measuring a capacitor. So this is a plus and this is a minus. What will happen to the capacitor is that we charge up our plate and we charge this one up. And what happens when it's full?
No current flows.
No current flow. So what you will see is that at first, your R is equal to E divided by I. Your current will be very, very big when it's filling it up. So you have E divided by big, which is about equal to 0. So your resistance will look like it's 0. But then once it's completely charged, what will your current be?
0.
0. So this is now replaced by E divided by 0, which is no longer 0, it is infinity. So what it will look like is you'll do this. Your resistance will follow a curve that looks like that over time. So if you see a resistance that starts at 0 and then goes up to infinity, that means that you've got a big capacitor that you just charged up in the circuit. Okay, a device used to measure current is known as an ammeter. That would be like this. It goes in series with the circuit because it actually has to measure current flow. Now, this is actually very inconvenient a lot of times because let's say you have a circuit that doesn't have a break in it, right? Well, how do you break it?
Amp clamp.
Yeah, you might have to actually cut something. So there's another way to do this. We sort of looked at it a little bit yesterday, which is that you have something that looks like this, which is a toroidal core that picks up the magnetic field generated by the current flowing on the wire and puts that through a meter. And that's known as an amp clamp. And what it does literally is it picks up the magnetic field, measures it, and figures out how big of a current is making it. So it's an indirect way of measuring it. The nice thing about it is that when you're done, you just do this and disconnect it and it goes away. And you never had to do anything to your circuit like cutting a really big wire. So that's an inductive ammeter, as it's called. For electronic and radio use, you do something called rosin core solder. Rosin is the same stuff that if you play a string and bow instrument like a violin, it's the same stuff that you rub on the bow to keep it nice and slick. A cold solder joint would be something that looks grainy or dull. In a cold solder joint, it's still something that melted, but if it's a cold solder joint, that means that it didn't completely melt to all the surfaces and you have a mechanical connection, but not necessarily a good electrical connection. Okay, Next section. FM operation, repeaters and good old stuff like that. All right. What's a repeater again? What is a repeater?
Transceiver.
It's a transmitter and receiver simultaneous. And it transmits on one frequency and receives on another one. That's a repeater. And it automatically and simultaneously does this. Now, what types of stations can automatically retransmit signals? That would be a repeater. But there are other ones. There is something called an auxiliary station. An auxiliary station can be a station that receives signals coming from one place, like on a directional antenna, and sends them to another one. This is very common, as we were saying, in linked systems, where you have a microwave link using the microwave bands, or this could be UHF, where you basically have a point-to-point link between two different stations. So you need this auxiliary station to always retransmit the signal.
Is that a safety issue? Just using auxiliaries for microwaves?
No. I mean, usually it's up on a mountaintop or a tower or something. A space station, for instance, the International Space Station. That's anything 50 kilometers or higher. So a satellite floating around can have an uplink and a downlink, and that can actually function as a repeater as well. And in fact, the International Space Station has an onboard repeater. Which of the following describes a linked repeater network? Linked repeaters are basically a bunch of repeaters that are, let's say, here and here and here, and each of them transmits and receives, and they are also sharing information either over the internet or via radio links, that anything that any one of them receives will be retransmitted on all of them. And anyone who can access any of them can get into all of them. So people who are way over here can talk to people who are way over here. A common repeater frequency offset in the 2-meter band, 600 kilohertz. That is the most common anywhere you go in the United States and Canada. On the 70 centimeter band, the offset is 5 megahertz. Okay. Subaudible tone. There we go. We're now talking about CTCSS, Continuous Tone Control Carrier Squelch System. CTCSS, also known as PL, that's the Motorola trademark. This is a subaudible tone, of which there are 38 of them, from 67 hertz up to, I think, 253 hertz. And there are 38 of them. And those allow you to basically superimpose a low volume, low frequency tone onto your transmitted signal. That can be used to open up a repeater squelch. So continuous tone control carrier squelch system. So let's say you can hear a repeater really well, but no matter how hard you try, you can't get in. Okay, so you're transmitting on the wrong frequency. Well, I've done that myself. You transmit on the wrong frequency. You don't have the offset set correctly. The repeater has no idea that you're even there. If you don't have the right CTCSS tone, let's say the published frequency is 100.0 hertz, and you are transmitting with 97.4 hertz. Repeater will hear it and reject you. The other one is something called DCS, which is a digital code squelch. These are analog. This is digital. It's basically a series of tones that represents a certain code. So this would be something like D023, D026, and that's continuously sent and repeated during your transmission. So long as it's there, it's just another version of the CTCSS, except it's a digital code. Just another thing. And that's again known as DCS. If your station's not strong enough to keep a repeater squelch open, which of the following can you do? Well, it might turn out that you and the other station are really close together. So let's say the repeater is way over here and here's station A and station B, and they're both trying to talk through the repeater. Well, it might turn out that, again, they're only a mile apart, in which case listen on the transmit frequency for the repeater, listen for the receive frequency of the repeater. And it might be that you find out that you're really close together, and then you don't have to use the repeater at all. You can just go directly. So you listen on the input frequency of the repeater, listening to what the other station is transmitting directly. This is also known as reverse split. Normally, you would be split frequency. You would be transmitting on one and receiving on the other. By going into reverse mode, you listen on the other frequency for other stations that are transmitting into the repeater. If you're breaking up on voice peaks, that means you have too much signal going out, which means you're speaking too loudly. Let's see. All right, who here? KO6BOB, KO6BOB, N7JI. Bob, are you there?
Go ahead.
All right, KO6BOB, this is N7JI. How you doing, Bob?
Doing well. KO6BOB.
All right, well, I'll talk to you later, N7JI. So how do you call another station on a repeater?
With your call sign.
With their call sign and your call sign. Now, if you're just saying that you're there looking for somebody to talk to, you would just say, this is N7JI listening. Throw out your own call sign. That indicates that you're there, and anyone else who might want to talk to you can talk to you. Okay, station transmitting and receiving on the same frequency. That means that there's no offset. That's known as simplex. Why are there simplex channels designated in the VHF UHF band plan? The main reason being that if there were repeater users there and there were simplex users there, repeater users would be transmitting and not be expecting to listen to anybody on the same frequency. So this basically allows stations that are close to each other to select certain frequencies that they know will not be used by anybody else on a repeater. So if they're within mutual communications range, you can choose to use simplex. And the most important simplex frequency that there is on VHF UHF is 146.52. This is the national simplex calling frequency in the United States and Canada. This is if you drive into a town and you don't know anybody and you don't know where the repeaters are or anything like that. If you make a call on 146.52 simplex, there's a good chance that somebody will hear you. Almost everybody who has a radio that's scanning is scanning this frequency. So that's why this is on the test. 146.52 megahertz is the national simplex calling frequency.
Is there a national emergency frequency? Say I get lost hiking and I want to call SOS.
Nope.
Nope.
This is it. This is the most likely frequency that you're ever going to hear somebody on simplex.
Okay, thank you.
All right. On the HF bands, we're on to high frequency, page 70. So we use this on VHF also, not on repeaters, but what does CQ mean? Has anybody here ever been on HF?
No.
Nobody. Wow. Oh, cool. Okay.
I may have been during some contesting, but I don't know if it was HF or something else.
All right. So CQ.
Is anyone there?
Yeah. CQ means, is there anybody there? CQ means, is there anybody there looking for somebody to talk to? I'm calling anyone. Before you start calling CQ, the things you have to do are look and see, listen to make sure that you don't hear anybody on the frequency. The other one is to make sure that you're allowed to be there and call in the first place based on your license privileges and the band plans. And then finally, you ask and see if the frequency is in use. Let's say that I'm here and there's another station B and there's another station C, and I can hear station B. So that's a good propagation path. There's another one between B and C where they can hear each other, but I cannot hear station C. And station C has been rattling on for the last 5 minutes. Well, station B is actively talking and listening to station C, and I can't hear him at all. To me, it sounds like a dead frequency. So I just start calling and calling and calling. What I've just done is I've now interfered with station B. So the first thing I do is I say in Morse code QRL, which means is the frequency in use. If I'm doing it in English, I would say is the frequency in use, N7JI. If the frequency is in use, station B would say, sorry, old man, the frequency is in use. And I would just scoot off and find another frequency to use. How do you respond to a station calling CQ? You use their call sign and then your own call sign, indicating that you're calling them and that here I am. When do you have to identify your station? Even if you're only making tests, you have to identify every 10 minutes and at the end. And the easiest way to identify your station is just by using your own call. Okay, some Q signs that we have to know. Okay, QRM. We only have to know 2 of them.
Real quick before we get into
Yeah.
that, how does that change when using a club call sign?
It depends. Who's the control operator? There has to be a control operator. So let's say, okay, so let's say in my case, W7PXL is our radio club. Everybody there, if I'm defined as the control operator, and hi Kent, if I'm defined as the control operator, I'm responsible for everything coming out of the station. Everybody else who's using the station is is basically, under my auspices. If something goes wrong, it's my fault.
Okay, that makes sense.
Yeah.
But the 10 minutes, then you would just use the club call sign rather than a person.
You would
if
just
you're
use the club
operating
call sign.
under the club.
Right.
Okay.
What Q signal indicates you're receiving interference from another station. That would be QRM, which is man-made interference. I see Kent raising his hand. Kent, how about 1 more minute?
Yeah, I just wanted to comment on this point about call signs and identification.
Okay.
Let's not confuse this. If you're using a call sign on a frequency, regardless of whether it's a club or personal call, if that's the call sign you're operating with, like if you're operating it from the club station using the club call sign, you must identify every 10 minutes with the club call sign.
Right.
If you're using your personal call sign, you use your personal call sign. I don't want you to confuse the notion that you're at the club station using the club call, but you're the operator, so then you also identify as your call sign. If you're operating as under your call, you can, or you would. But if you're operating under the club call, you identify with the club call. Sorry.
All right, thank you.
Actually, I got a question. So,
yeah.
So you're saying you have to give your call sign every 10 minutes. What if you're just sitting there and listening? You don't have to.
You don't have to do anything.
But if you're in the middle of talking and you're at 9 minutes, give your call sign.
Yeah.
And then go on talking.
And interestingly, you have to give it every 10 minutes and at the end, but you don't at the beginning. There's no requirement at the beginning.
Huh.
Just every 10 minutes and at the end. Now in Canada, there's actually a little bit of a difference. You need to check the rules when you're going for your Canadian license, because it's not every 10 minutes and at the end. And I think you may have to identify with a location or something once an hour, if I remember right. I don't remember exactly though. I do remember following the rules and reading up on it when I was operating in Canada, but I don't remember exactly what it is.
So Scott, quick
So
question.
I live near one of the few parts in the world where you can drive south into Canada, at least in the US.
So Detroit?
West of Detroit, I think.
Okay.
But so if I get my license here in the US, if I drive into Canada, would I have to have a Canadian license and call
Nope.
sign? Or
Nope. You'd be, if you're in Ontario, which I think you are, you'd be VE3/ whatever you are. Or you'd be your call sign / VE3.
You just have to follow the Canadian rules.
And you have to follow the Canadian rules,
okay, thank you.
which are largely the same, but you have to see. But
Scott,
yeah,
quick
we have automatic reciprocity with Canada.
All right, thank you.
Yep. Okay, changing frequency, that would be QSY. Those are the only two Q signals you need to know, QRM and QSY. What is a band plan? A band plan is essentially the FCC. We don't want them to tell us what to do with our frequencies. We don't need them to tell us what to do. The way we maintain order is by creating band plans, which are gentlemen's agreements saying this is what will be done, where and when and how. So if everybody follows those band plans, it keeps the phone operators in one part of the band and the code operators in another part of the band and the digital operators in a different part of the band, so they don't interfere with each other. There are only a couple of areas where there are actually legal precedents saying the FCC has said that you will only operate this mode in this place. And I can only think of 3 of them offhand. One of them is on the 2 meter band, one's on the 6 meter band, and one is on the 1.25 meter band. And one sec, let me just do this last one. Which of the following applies when 2 stations are transmitting on the same frequency and they interfere? Common courtesy prevails. Nobody has an absolute right to a frequency. No one owns a frequency. Go ahead, Kent.
Yeah, thanks, Scott. Yeah, one of the areas you have to be careful is frequencies that are used for space command and remote control operations. So you really want to follow the rules there because you don't want to cause a satellite to go out of control or cause a remotely controlled vehicle to do the things that it shouldn't be doing.
Okay, so everybody notice on this chart right here, at the very bottom end of the 6 meter band and the 2 meter band and the 222 band, there's that little red area. On the 6 meter band and the 2 meter band, those red areas are specified by law that those will be the only modes that are operated there. They don't even show it on this particular chart. On the 1.25 meter band, there is also, let me see if I have it here. Here we go. On the 1.25 meter band, notice on this chart, we have this little area between 219 and 220. This came about when we used to have the 220 to 225 entire band. And a package delivery company came up with a system they said, well, they needed access to 222, and in exchange, we would get 219 to 220. That is for fixed digital message forwarding systems only. I don't know anybody who uses those frequencies, but I assume that would be something like, data forwarding, packet radio, things like that. But in that particular band, that's the only thing that's allowed to be used. Kent, you're up. Kent, I see your hand up.
I think you just loaded up from before. Hey, can I ask a quick question?
Yeah.
Talking about digital packets. Why in the layout of the manual there, it talks about generally that packet digital modes is packet PSK 31.
Okay, totally different. PSK. So what's the question?
Well, the question is, in the layout of the manual, it says digital modes. And the way it's entitled is, it's all encompassing packet PSK 31. Whereas you've got all different types of modes, but
well, I mean, okay, so if we were actually look at the different digital modes that exist, okay, there's Clover, there's PSK, all different varieties of PSK. There's radio teletype. There's Morse code. Technically, that's a digital mode. There's WeFax, which is weather fax. There's fax. There's technically SSTV, which is kind of a slow scan television, although I guess sort of it's an analog. So I'm going to erase that one. There are probably 20 different versions of RTTY. There's probably 20 different versions of PSK. There's QPSK. There's APSK. I mean, there are so many different things. There's Hellschreiber.
What about DMR and WSJT? Oh, they fall in FT8.
There's FT8. There's JT65.
WS.
JT9. WS.
Fusion.
Well, Fusion is Fusion is digital audio. There's let's see, there's Whisper. And then you also have all the digital voice modes. So there's DMR, digital mobile radio. There's Yaesu Fusion. And what's the ICOM version again? What's the ICOM? D-Star. These are all different digital modes.
Okay.
These over here on the right are digital voice. And these on the left are digital, like computer to computer. And that's only a small summation of them. I mean, there's more than that.
Those digital voice ones, are those proprietary? Like the ICOM is only going to communicate with the ICOM, or?
Yeah, Yaesu Fusion only communicates with Yaesu. D-Star is an ICOM that Kenwood has joined onto. And DMR is the most open of them. It's not completely open, but it's the most open. And Kent, you're back, right?
Yeah, I think so. My computer went a little crazy. Sorry about that.
Okay,
It's-
well,
It,
all right.
it had some jet lag traveling west to east.
Yeah. All right. Take it away, Kent. We're going to take a 5-minute
Oh.
break as soon as you're done. So,
All right, great. Good morning, everybody. Sorry to interrupt and be disrupted, but I'm Kent Petty. I'm KL5T. I'm the chairman of the Anchorage Amateur Radio Club, DEC. And for many of you, we're who you're going to take your exams with this afternoon. So good luck on it. So how this will work. We're scheduled to start exams at 1 o'clock Pacific time. So whatever that equates to your time, you can make the adjustment. We have quite a few of you, and we're never quite sure how many DEs will be showing up to assist with the session. DEs are volunteer examiners. And so how we like to do this is we will basically ask you to be ready. We're going to call you when it's time to check in, and we'll have you join the Zoom call with your primary device. And once that's in, we'll have you bring in your secondary device. And once you're in there, then we're going to move you into a preparation room. Okay, so we'll send you a little request on Zoom to move to a breakout room. So we'll move you over to there, and we'll get you set up for the exam to make sure everything's working right. And when a team is ready, we'll move you into that room to take your exam. So everybody who's registered, we have the phone numbers that you provided, and we'll be calling you on those phone numbers. Please don't join the Zoom call until we give you a ring. Okay, I'll just say it again, everybody, because otherwise it could get a little clogged up. If you just wait till you receive the phone call from us, then join the Zoom, that'll be perfect. Now, are there any questions?
Yes, I was messing around with Zoom last night to see how you guys are wanting to use 2 cameras. Do I have to like log in as a guest or something? I'm not sure how to do that because when on my computer it wanted me to go ahead.
Yeah, okay. So very good question. So just join the Zoom link, just like you did for Scott's session here. Okay. The thing is, you'll join that Zoom link with each device. Okay. You can join the same session with the different device. With the Zoom link you have, it works perfectly. Trust me, we've done thousands of these. Does that make sense?
Not really.
Okay, so let's imagine this. You're at your, well, no, just, it's really simple. You're at your computer, open the email that has a Zoom link in it, click on it, you will open Zoom and you'll go to the session on your computer.
Okay.
Okay, let's forget about your computer for a second. Now go to your phone. Can you access your email on your phone?
Yeah.
Okay, open the email on your phone, click on the Zoom link, you will join the session.
Okay.
It works
All right.
perfectly. Now, the key point is on the second device, anytime it asks you for connection to audio, any audio connections, say, no, 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 we don't want any of that because it'll be bad for everybody. We'll get feedback and that goes, okay?
Okay.
All right. And then what we'll do in the tech room is we'll get you set up because we want that second camera to be able to sort of give a side view, but really gets a view of the screen that you're taking your examination on. Okay, so just kind of think about that and be prepared to sort of get that in that position, but we'll work with you and set up to get it set right. Don't worry.
Okay.
We always get it worked out one way or the other. Okay.
If there was an agent there.
Go ahead, Lucy.
Is there a way to request being kind of at the end of the line?
Yeah, we could put you at the end of the line.
Okay.
Yep.
I've got animals to take care of and a place I have to run to, and then I'll be back.
Not a problem. Lucy, right?
Yes.
Okay, good.
Good morning or good afternoon, actually. Can you hear me?
I can hear you, yes.
Okay, I was one of them that sent an email yesterday saying to see if I could be rescheduled. I don't know if that's
Okay, yeah.
possible.
Yeah, you could certainly be rescheduled. So all you need to do is, did I not reply to your email?
Honestly, I didn't check. I've been all day trying to set this up, and I'm actually on the course, but I'm the road. I'm driving.
Yeah, I understand. That's not a problem. If you need to reschedule, that's not a problem. Just go to our website and I'll get that link. We'll drop it here on chat. If you need to reschedule, just let us know. But the big thing is just register for another session. You don't need to pay again, and you don't need to do the exam agreement form again. You just need to pick another session. As long as we know that you're not going to be at this one, we'll just pull you off of it. It's not a problem. But you can sign up for any other session.
Okay, so there will be a possibility you could email me that other link so I can register again after today.
Yeah, I'm gonna do it. Actually, I'm gonna drop it in. Before I drop off this session, I'll drop it into the chat so it's available to you guys, okay?
Okay, like again, I'm driving. I'm not gonna be able to do anything with it now, but I'll try to get
Oh,
it.
I understand. So here's the deal though, is I'm not sure who I'm talking to.
Noel, my name is Noel. I'm the third one on the list. Noel Bobbitt. I'm the third one on the list. to take the-
Yeah, Kent,
Yes.
I just sent it to your, I just sent it as a direct message to your chat.
Okay, thanks. I'll get that over to you. I'll send you the link. All right?
Thank you, appreciate
No
it.
problem. No problem.
And how frequently do you do these exams?
We test twice a day, Monday through Friday, or Monday through Saturday. We test at, it would be effectively 1:30 Pacific time, or I'm sorry, 10:30 Pacific time and 2:30 Pacific time every day. That's, or Monday through Saturday anyway.
I have a question.
Yes.
How will I know what time I will be testing? Is there?
You're gonna get.
Oh, go
No,
ahead.
you're gonna get a phone call. This is a fluid situation to
Yes.
some degree because we only have so many volunteers. And
Okay.
it takes everyone a little bit different length of time to get set up and to take their exams. So we're going to get you guys, trust me, everybody wants to get through as quickly as possible. So we work as quickly as we can. Usually if there's probably going to be a 2-hour window.
Has anyone, Kent, have you asked if if anyone has a time constraint and like needs to go early or needs to go late?
I do.
Well,
Yeah, I'm in New York area, so we're like 3 hours ahead. So yeah, if Lou Macario could, I got family stuff I gotta take care of, so.
Okay. Just drop Scott, send that to me. I'm not in a position, I got on here without having my notepad. I'm actually, I just arrived at a vacation location here on the East Coast. So
Dude, where
I'm
are
I'm in
Ah,
Florida.
you? Oh,
We traveled last night. It was from Alaska.
did you see Rich?
Wow.
Have you seen Rich down there? He's in Georgia.
I'm in Florida.
No, I know, but you know, you're close, right?
a lot closer than Alaska.
Oh, man. Well,
Where in
enjoy-
Alaska are you?
Near Anchorage, Eagle River.
Oh, okay. Lived in Fairbanks.
Oh, yeah. Well,
Ugh.
you had to want to live there. That's a little chilly. Of course, it's cold right now up in Anchorage, even if we're hitting 20 below right now at night. So
Oh,
I'm glad to be here.
Yeah, I bet.
So, when you will call and I'll answer on my cell phone and I connect to Zoom at the same time, or will I hang up the phone call with you and then connect to Zoom?
You'll hang up the phone call. I'm going to call you and say, please join the Zoom call now. See you in a minute.
All right. And when I hang up, then I put my phone in my tripod and point it towards my testing area. Is that correct?
Yeah, that's what's going to happen. Now, know where you're going to set it, because one of the things that'll happen once you get into the test room with the VEs is they're going to ask you to take that second device and they're going to ask you to swing it around the room real slow, like because they need to take a look at the examination area. Okay. And then so they'll even have the 360-degree look at the room. And then they'll even have you point it to the ceiling. They'll have you point it down to the floor by your feet. They'll take a look at your desktop. And then once they're all happy, then they'll say, okay, go ahead and put it in its final position.
And I have practiced this and my phone has accidentally hung up. So
Well, don't worry. We have technical issues from time to time. We're pretty adept at working through them. It'll be okay.
all right.
Not to worry. Not to worry. We will help you through it.
I see Brick with a hand up.
Hi, Brick.
Hello, Brick.
You're muted right now, Brick.
There we
you go. Brick. Hello, Brick.
Unmuted, but I can't hear you, Brick. All right. Well, he had asked a question about using Zoom through a browser, and
we don't care how you use it. It's up to you.
Rick can message me and I can relay the question if you want.
Sure.
Okay.
What's the question? Oh, what else? Oh, listen, for taking the exams, you don't want to try to take the examination on an iPad. They don't multitask well. You'll have the exam, you'll have Zoom up and then you'll switch over to the exam platform and it'll drop the Zoom video and audio. Okay, so you want to use some other device. Typically, most people use a laptop or their desktop computer, that sort of thing.
All right.
Was there a question there, Quinn? You're muted.
My space bar isn't working right to unmute. I just got the question from Bricken, and that's is the exam not at 1 p.m. PST, 4 p.m. Eastern for everyone in the class?
Got it. Okay, so we're going to start doing exams at 1 o'clock. I'm not sure how many volunteer examiners we have. We need 3 VEs per examinees. Okay,
I think we had
right
16
now,
as of yesterday.
Yeah, as far as the number of VEs we're going to have, it's probably about in that neighborhood. So we'll be able to run about 4 testing rooms at a time. Okay, so we'll whittle through y'all. So he needs to stand by for the phone call. Okay, when he gets the phone call, then we'd ask that he join the Zoom call. So just relax, study, and if you need to just keep studying until you get the call, and then we'll get you in the test. Okay.
And then I had a question as well. I don't necessarily have, I just realized I'm at home and not at school. I don't necessarily have like a clean desk space to take this on.
Bathrooms, kitchen tables, dining room tables.
Okay. I would do kitchen table. My one concern is I remember in the rules and regs, no one else can walk into the same room. So if people are walking in and out, how much of an issue is that?
Caution tape.
It's an issue. Tell them you're taking a test, don't come into the room.
Yep.
Go to your
Okay.
garage, do whatever. If it's nice
Winter in
outside, go
Michigan, I ain't
outside.
trying the garage, but I will figure something out. All right, thank you.
Well, geez, I live in Alaska. I've got a heated garage. Come on, man.
I would have to get a fire going in the stove. It's not a connected garage, so.
All right. Yes, you need to be isolated. You need to be by yourself. Don't let anybody come into the room. We can't have that, okay?
What
all
about
right, thank you.
bookshelves above the desk? Do we have to clear that out too? Or just a
We're gonna
workspace?
take. Okay, so we're gonna pretend you're an examiner and you have to look at the room that somebody's taking an exam in. Okay, so we're gonna look at the room. If it looks okay, if it's just the spines of books, nobody's gonna care. If you got posters of frequency charts and whatnot, that's gonna be a problem. Okay.
Okay,
So
sorry.
just pretend you're an examiner, and that should help you answer most of your questions.
Is it acceptable to have the laptop that we're taking the test on just in our lap as opposed to on a desk?
Well,
Be able to see your face. So
yeah, it needs to stay focused on you, on your face. So when you are taking the exam, what we do ask is that you stay focused on the computer that you're taking the exam on. We don't want you looking around all of this kind of stuff, because then we're wondering what you're looking at, right? So we want you to stay focused. So if you can hold your dead still, I guess that would be okay.
Okay.
yeah,
great.
Ken, we've got 15 VEs on the list right now.
Okay, and there likely will be a couple more show up. So
Yeah.
we'll be running you guys through as fast
Quick as we can.
Yep.
But there's
And,
no time limit on taking an exam. So don't feel rushed.
Okay.
Please
Don't
accept our
worry,
thank
listen.
yous.
Yeah, and listen, everybody understand, we are on your team. We want you to succeed, and we want to make this a good experience for you. So, so what'll happen, y'all are gonna take your test today, and you all are gonna pass. And then we will file, well, actually, we don't actually submit on the weekends because the FCC's got problems. We'll file tomorrow morning with the FCC, and within an hour after we file, call signs should be issued. Or I know there is a novice in the group, and you'll get your upgrade. Okay. If we were doing this on a weekday, you'd have your call sign within the hour.
Mhm.
They don't process on the weekend.
Kent, just so I can ask really quickly, we've got a Canadian here who wants to be taking a Canadian exam. I can forward him to Brandon, right? He does Canadian exams.
I can't speak to that at all.
Okay.
Sorry.
And how soon after we take the test do we know what the score is, whether we pass or not?
Immediately. Well, you'll at the bottom of the exam, there's a grade me now button. You'll click that. We'll see that you clicked it, then we'll approve the grading, and then it'll snap right up on your screen.
And then how soon can we reschedule if we didn't pass it then?
As soon as you want.
All
If you
right.
only miss by 1 or 2 questions, and you tell us that hopefully everybody's been taking sample exams. And if you're passing sample exams, or test exams, then and you're doing well on those, we'll be willing to retest you. But if you tell me I've been taking practice exams and scoring 60%, we're probably not going to retest you. The minimum passing score is 74%. That means 26 questions correct. Okay.
All right. And then
Out of 35.
you retest Monday through Saturday, 10:30 Pacific time and 2:30 Pacific time.
That's right. Yeah.
Okay. Thank
But
you.
you're not going to need that because you're going to pass today.
Well, I'm hoping, but
Knock
you
on
know.
wood.
Okay.
Go enjoy the sun, Kent.
Yeah. Anything else? I just want to make sure we have Scott, were you able to send me, you sent me information
I did.
on 2 individuals, right?
Yep, I did. It's in
Okay.
your email.
Okay. Oh, you sent it to email. Very good.
Yeah.
I'll tend to that. Okay. All right. And Lucy, you wanted to test at the bottom of the list, right?
Well, I mean, just towards the end. I
Got
just
it.
I need a couple hours to run an errand and take care of some animals.
Okay. All right. Well, we will give you a buzz. You'll be at the last of the list.
Okay, thank you.
All right. All right. If there's nothing else, oh, a couple other minor things. You can use a calculator today. It needs to be a handheld, separate calculator. I can't use a device on your, you can't use your phone or software on your computer. And you'll have to show the calculator to the team. Make sure you've got your government issued photo ID with you because we'll ask to see that. You can also use a sheet of scratch paper today. You'll have to hold it up to the screen and show the team that it's blank, okay? Also, no smartwatches and no earbuds today for the exams. Okay. Okay. Good luck,
Ken.
everybody. Oh,
Yeah.
excellent.
Thank you very
Good.
much.
Go enjoy the
Thanks for
sunshine,
doing this,
Kent.
Scott.
Yeah, thanks for doing this, Kent. And by the
All
way,
right, see you
Hannah
later,
is
guys.
coming. Hannah is coming.
Oh, excellent.
Yeah,
Cool.
I know. I didn't even
Hannah's
have to
just-
push. I didn't even
Hannah's
have to push.
Scott's, Hannah's one of Scott's daughters. I
No,
think.
I only have one.
It's one. Anyway, she's way cooler than Scott, just so
Yeah.
we're clear. Yeah. See you later, Ed.
See you, Kent. All right.
Okay, bye, buddy. Bye.
All right, everybody good for a 5-minute break? We might push a little bit past noon just because that was about 15 minutes. So, but we're gonna aim for noonish. 5-minute break, everybody.
Okay.
My butt could use a rest
Yep.
or a stretch.
Yeah.
All right. Any questions before we get started again? Is everybody having an okay time? I'm not going to say a good time, but everyone having an okay time?
Yeah.
I'm having a good time.
Good.
Even though I'm in my car, I'm still here.
Excellent. Where are you right now?
Right now, I'm in Nanuet, New York.
Where?
Nanuet, New York.
You're in Nanuet, really?
Yep.
I've been to Nanuet. That means you just passed Spring Valley.
Yes, sir.
And you're coming up and you just passed Suffern.
Yep.
Yep.
I'm coming from Tenafly.
Tenafly. Yeah.
Where you going? Palisades?
No, I'm actually staying here in Nanuet.
Oh, you said, okay. Yeah, it's 10 minutes from us.
I grew up, I was born in New York City.
Oh, you're a New Yorker.
Yeah. And you know, it's funny, if I get around a bunch of New Yorkers, I start talking like that really, really quick.
I'm born in the Bronx, so yeah, I'm from New York too.
I was actually born in Queens, in Fresh Meadows.
Ah.
Yeah.
I've got a little question before we start.
Yep.
At the end of all this, would you be, and it might not be possible, but would you be able to think of a couple of different systems that a person could buy to start out with?
That's too hard of a question to come up, too hard of a question to answer.
Yeah, as of right, it might be. I just
Well-
don't know where to start.
Well, okay.
I've got a little handheld I bought at a Hamfest.
Well, it really, the answer comes down to what do you want to do?
Well,
So-
I'm up. Yeah, I'd like.
991 Yesu.
Well, see, I've got my Yaesu handheld. I've got an Anytone DMR handheld. I've got my old Yaesu handheld. I've got my ICOM 7300 in the garage. I've got a mobile radio. I've got, you know, I mean, it depends what you want to do.
Okay.
We can talk about that.
Yeah.
There's
Okay.
there are more answers than there are people giving them.
I bet.
So
I've been to Hamfest. I've seen how many. That's why it's so confusing. There's just so much out there.
you need to find somebody who's willing to be on the ground with you, who will answer questions on the fly
Okay.
or on the phone, you know. All right, so we're into
That would be an Elmer,
that would be
right?
an Elmer. Yep.
Yeah.
All right, we are into public service and emergency communications. Okay, ARES, Amateur Radio Emergency Service. That is an ARRL organization that's set up that basically conscripts hams and equipment into public service. So you basically volunteer for public service. That's amateur radio emergency service. This is very similar to amateur civil emergency service, or RACES. So there's ARES and RACES. The main difference is that with ARES, you sign up with the ARRL, and with RACES, because that word civil is in there, you actually sign up with a civil defense organization. So they're both for emergency management, but one can be deployed by the ARRL, and the other one, you basically sign up with your local civil defense agency. So they both use ham frequencies and ham equipment.
Okay.
That's a similarity between the two.
And that's coming in the exam.
Yeah.
Yeah.
All right. NCS is a net control station. And so if you're operating in a net is short for network. Basically, a network is a group of people who basically set up to communicate with each other for whatever reason. I mean, we have a Friday lunchtime net where we discuss what we're having for lunch. It's basically just a chance for people to get on the air and talk to each other and practice being on the air and talk about lunch. So it doesn't have to just be for emergencies. An accepted practice for an amateur operator who has checked into a net is to stay on frequency until you check out or until you're released. And also, you don't talk until somebody asks you to talk, keeping the frequency clear. how do you break into a net with emergency traffic? You would say priority or emergency, and then give your call sign. So basically saying, this is not routine traffic. I have an emergency. This is something that typically would happen in the case of, like, you know, you're in the middle of an earthquake, and you know, so you have an evolving situation that has to be administered to. Traffic is technically speaking is formal messages exchanged by net stations. That is traffic. Traffic is basically information that's carried by the network. Good traffic handling is passing messages exactly as received. So if you miss the word not, that's a big deal. You know, the hospital is not full versus the hospital is full. Those are two very different things. Let's say that you have an unusual name that a lot of people would not necessarily know. So I'm going to use one of you guys as an example. I'm going to use Schattenberg, because there are possibly different ways to spell Schattenberg. It could be B-U-R-G, it could be S-H versus S-C-H. So if I was sending the name Schattenberg across a net and I was doing it orally, I would say Schattenberg. I spell Sierra Charlie Hotel Alpha Tango Tango Echo November Bravo Echo Romeo Golf. I would do it phonetically using the ITU phonetic alphabet, so that it was 100% clear how the spelling was supposed to be.
So you could go to the ITU.
If you just look up,
website.
if you just look up ITU phonetic alphabet,
Okay.
Alpha Bravo Charlie Delta Echo Foxtrot Golf Hotel, and it's there are different phonetic alphabets in the world, but that's the one that everybody uses.
Okay.
And that was Indio Tango Uniform?
Yeah.
I think there's a copy of that in one of the documents you sent us.
There probably is.
Oh, okay.
Okay. The preamble of formal message traffic. The preamble is the information needed to track the message, saying who it came from and where it's going. There's also something called a check. So if I were to send a message that says, the hospital is full, your check is 5. Well, the hospital is full. That's only 4 words. That means that there's a message, there's a word missing there, and I better ask for a repeat. The check is the number of word or word equivalents in the message. Okay, when do the FCC rules not apply in the operation of a ham station?
They always apply.
They always apply. So when are you allowed to not follow the rules and operate outside of your privileges?
Never.
No, that's not true. You are allowed to.
Well,
In
in
an emergency.
In the case of a bona fide emergency. So human life or protection of property. If either one of those conditions exists, you're allowed to operate outside the bans. So basically the rules say you have to follow the rules, except when you don't have to follow the rules. So, but that's in the rules. So you're still following the rules. Okay. We're on to satellite operation. Okay, which amateur radio stations can make contact with an amateur radio station on the ISS using 2 meter and 70 centimeter band frequencies? So it's not common that we have a novice in class, but notice that the answer, we're on page 74, says any amateur holding a technician or higher class license. The reason that exists is because there are still novices in the world. Not many, but there are still some, and novices don't have access to those bands. So if you have a technician class or higher, you can talk to the ISS. Mode UV. And by the way, I would like to say that upgrading from novice to technician, as you're doing, is actually a really big step. And in my experience, I've only experienced one other person doing it. And like I said, a month and a half after that, she has her extra. So.
Wow.
Now, Scott, isn't there a break-off date that if you are a technician and you had your license, that you can be advanced to general?
You get a
without
general. Yeah, you
tests?
can get a general.
I don't know what
I
that
think
date
it's
is. but
1987, I think. I think it's 1987. There was another date in 1994. And I should really go back and look at the rules because that's in the rules, that's in the guidelines when you become a volunteer examiner. Okay, mode UV for a satellite, that would be U, UHF up and V, VHF down. So what are those limits on the UHF band? What are those frequency ranges for UHF?
300 to 3,000.
300 to 3,000 megahertz. And how about VHF?
30 to 300.
30 to 300. Okay, very good. See, I told you that would keep coming up on this in this class. I would keep asking. Okay, what mode of transmission is commonly used by amateur satellites? So the biggest one is FM, but that is not exclusively what is used. There's also single sideband and there's also CW and data. So almost any of the above. So satellites, they just have to be programmed to be able to use certain frequencies. What is an impact of using too much effective radiated power on a satellite uplink? This is most common when we think about, let's say that a satellite is listening in this certain frequency range. And this one's transmitting on this one, and this one, and this one. And these frequencies are moved over to here and then retransmitted down in that same pattern. So this one here is at the low end, transfers to here. This one transfers to the middle, and this one transfers to this one. So what happens if you transmit with so much power that you desensitize the whole receiver?
You block the other.
You block the others because the receiver can't hear the other stations. So a good rule of thumb is if you're doing that, you want your signal when you're hearing it on the downlink of the satellite to be about the same size, about the same strength as the beacon. The beacon is basically the satellite saying, here's my call sign, here I am. Here's my call sign, here I am. Here's my call sign, here I am. That's all it does. Here's my call sign, here I am. Most of our amateur satellites, and there are many, are in something called low Earth orbit. So that's LEO or LEO. Now, so here's the surface of the Earth. Low Earth orbit is about 200 miles up. If we think about geosynchronous orbit, how high is geosynchronous orbit?
Say 500 miles.
22,500 miles. Okay, so why are most of our satellites so low?
So we can bounce off of them.
Yeah, but it would be, the problem then, of course, is that they're moving really fast, which means that typically a satellite in low Earth orbit passes overhead, and from there to there is about 9 minutes. Ideally, we would have it directly overhead. And at that altitude, you could cover a huge range. So why is it that most of our satellites are at low Earth altitude, low Earth orbit altitude?
Less expensive.
Much less expensive. That's right. You only have to get something to 200 miles up. It takes a lot of rocket fuel to get up to 22,000 miles up. That costs a lot more money.
I think they now say that you have to be able to dispose of the satellite also, right?
Oh, geez. Well, I mean, that might be that, you know, it does a re-entry and burns up in the atmosphere. You know, so if you can slow it down and have it burn up, then that would probably count. Okay, a satellite beacon is a satellite transmission that contains status information. All right, here I am. Now, I would like to point out that there is actually one geostationary satellite for use by hams. Unfortunately, that is over the Eastern Hemisphere, not the Western Hemisphere. And it covers all of Europe, all of Africa, most of Asia, and the very eastern part of Brazil. And it was put up by the, I believe, the Qatari amateur satellite community. So they managed to get an expensive ride up to a high altitude and found a place to put it. And it's sitting right over the Eastern Hemisphere, which means that we can't use it. Too bad for us.
I now have a reason to vacation to Europe.
Yes, exactly. Okay. Well, actually, yes, if you're going to do that, but I do want to point something out, that the extra class license translates to full CEPT licensure when you go to Europe. Any lower class license does not typically translate to anything. So if you're going to travel around the world, get your extra class license.
Good to know.
Yep. Okay.
To be
Go
to
ahead.
be a volunteer examiner, what class do you have to have?
You can be a general. If you're a general, you can give technician exams.
Okay.
If you're an extra, you can give anything.
Okay.
Okay. What information is contained in telemetry from a satellite? That would be health and status of the satellite. My battery is at 80%, full sun, 22 degrees Celsius. Everything's good. So that's information coming in from a satellite. And who can receive telemetry from a satellite? That would be anybody who has a receiver. You do not need a license to listen to a satellite or anything else for that matter. Which of the following are provided by satellite tracking programs? Okay, so you have, I'm going to share the AMSAT website. Okay, so here's AMSAT. AMSAT stands for, has anyone ever heard of AMSAT?
Mm-mm.
Okay, AMSAT is the Amateur Satellite Corporation. And so let's say, what does it look, where is the ISS going to be? Over my grid. Here we go. Here are the next 10 passes. So basically time, azimuth, and elevation of the start, maximum altitude, and end of a pass. So we look at this particular pass. It's it's about 45-degree altitude. It shows up in the northwest, disappears in the southeast, and it's going to be almost 11 minutes. That's a good pass.
Mm-hmm.
And let's see, where is the satellite? This will actually show the current location and what its next passes look like. So here it is right now at lower left. It's going to pass over us, and then it's going to proceed a little bit further west. The pass after that will probably pass directly over the northwest. The other thing is apparent frequency of the satellite transmission. Has anyone ever heard Doppler shift? I guarantee almost everyone
have.
heard it at some point. All right.
Yes.
Like when the fire truck drives by.
That is the frequency shifting as the satellite goes overpass. So your frequency has to change to continue communicating with it.
Right. Well, we've all heard what a fire truck goes by. As this pitch gets lower as it drives by.
Mm-hmm.
Well, believe it or not, a satellite at low Earth orbit altitude is moving at 17,000 miles an hour, and it's actually moving fast enough to compress the radio waves coming toward us and to stretch them going away from us up to 10 kilohertz if you're on the 70 centimeter band. So what that means is if you're operating through a satellite and you're transmitting on the 70 centimeter band, you actually have to transmit 10 kilohertz higher as it's coming toward you, and then 10 kilohertz lower as it's going away. Because it's going away, it's coming toward you and going away so fast that it actually stretches out the radio waves.
Is that something you would just do manually on your radio, or would you have your computer programmed to switch at the right time?
You certainly could. I usually I have those programmed into my handheld, but you certainly could. And if
So
you were
just-
really
you
tricky
just have
about it,
them- You have them as like adjacent presets on your handheld?
exactly. But if you were really tricky about it and you had a radio that was more continuously tunable rather than just every 5 kilohertz like this is, you could actually have it say, okay, here's the beginning of the pass, here's the end of the pass. And you could have it constantly changing the frequency based on where the satellite is and what the Doppler shift would be doing.
I got another little question.
Yep.
On your handheld, your antenna, can you take that antenna off and put the feed line from another antenna on it?
Yep.
Do you have to match anything? I mean,
Has to be the right connector. That's about
okay.
it.
But I mean, is there a special rating or anything like that?
No.
Okay.
Impedance wise, impedance matching.
Right. It has to be 50 ohms.
Okay. Okay.
Which of the following are inputs to a satellite tracking program? Those are known as Keplerian elements. Johannes Kepler worked on orbital mechanics, and he came up with these things, which are now called Keplerian elements, which define what an orbit looks like and where something will be at a certain point in time. So when I showed you that map of where the ISS is, that's based on the Keplerian elements for that particular orbit and where we are in time.
What
shift?
are those elements?
Oh boy. Okay. Let's see. Keplerian elements.
There's like 5 or 6 of them.
Yeah, here. Orbital elements. There are 6 Keplerian elements: eccentricity, semi-major axis, inclination, longitude, argument, periapsis, and true anomaly. And then there's mean anomaly. So there, there you go.
Wow. Okay, thank you.
Mm-hmm. And you basically have a starting time, a 0 time, and that determines where it's going to be at a given point in time that you are right now. Okay. Doppler shift, again, is an observed change in signal frequency caused by relative motion between the satellite and the Earth station. And finally, spin fading. Okay, this is usually true on bigger satellites. Most satellites, in order to stay stable, will rotate. Their antennas could be on one side of the satellite, and as it passes behind the satellite, as it's rotating, you'll get a fade. And then when it comes back into view, it'll get strong again. So that's known as spin fading. That's caused by rotation of the satellite and antennas. All right, contesting. One of my favorite things to do on the air. So contesting is an operating activity that involves making as many contacts and as many stations with as many stations as possible during a specified period. The one that we're in right now is called CQ Worldwide. It typically gets, I don't know, 10 or 20,000 participants around the world, some with very small stations, some with very big stations, and it's 48 hours long. It covers the entire weekend.
Wow.
Yep.
Can you pre-program people in your memory and just go through your memory?
What's the point of that? No, there's, you don't know where they're going to be.
Oh, okay.
Well, and what fun would that be? This is basically, has anyone ever gone bass fishing? I don't go bass fishing, but has anyone ever gone fishing? Like, so
once or twice, not specifically for bass most of the time,
okay,
but I fish.
But you never really know what you're going to catch, right? You have some idea what you might catch.
Yeah, that's about right.
So, okay, the idea with contesting is that we're going to look at a map of the world here. And okay, so notice we have the Earth, right? We're looking at a map of the world, and we have the day-night terminator. And remember, we discussed a little bit yesterday about propagation and daytime versus nighttime and solar radiation and things like that. So if we look at our frequency charts, what we'll find is that certain frequency bands do better when the sun is shining, and some of them do better at night.
Mm-hmm.
So what that means is that you can actually sort of predict what the conditions might be like. So a long time ago, the Voice of America, because their goal was to get those signals out into the world and spread, this is America. Some might call it propaganda. Every country does it, right? Okay, so one of the things that the Voice of America did was come up with this now available to hams propagation calculator, which I was running 25 watts and the antennas are fine. We're going to look at the propagation charts between the United States and Europe and go. This basically says at a given time, universal time, and a given frequency band, notice 80, 60, 40, blah, 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 where you have a good chance of making contact, or how good of a probability you have of making contacts with certain parts of the world. In this particular case, I've chosen Europe. And so I was on the 20-meter band this morning, and it was, let's see what time, 1500 universal time. and I was on the 20-meter band, which would be right here. So in this zone, kind of like lower left, where you get the brighter areas, and I worked a whole mess of Europeans. And last night I was on 40 meters and worked a few Europeans, and you'll see if you go to the 40-meter ring right here, you go to 0800, that's about midnight. Notice that there's a little yellow area down in here. So basically what this is really useful for is showing you what parts of the world you stand a good chance of talking to at certain times of day. Like for instance, from here to Japan.
Wow.
I worked a bunch of stations in New Zealand last night, right before I went to bed. And in fact, I did not expect them to be there, but there they were. And actually the maps show that that was probably predictable. So the idea of this particular contest is to work stations in as many different places as you can over a period of time. So you study the maps and figure out where your propagation might be favorable to try to work everyone. Okay.
Now, what do you do? Just CQ on different frequencies?
If you're a big station, you'd call CQ. If you're not, you just basically, it's called search and pounce. You're basically hunting.
Okay.
And what you'll find is that some of those stations, you learn something about whether or not propagation always works two ways, whether or not a station that's weak is really weak because the conditions are lousy, or because their antennas aren't very good, or because they're just simply not running a lot of power. So you'll sometimes find that a station that's really loud can't hear you call, even though they should be able to. And part of that could be that they're hearing so many other stations that they'll never hear you. It could also be that they've got local interference because they're in a city somewhere and their noise floor is up high and you're not getting above the noise. Or it could be that you have lousy antennas or you're not running enough power. So it's really very interesting for those who are, really scientifically curious, because you start to look at a lot of different factors. It's not just about, making a contact. It's trying to predict when certain things are going to be possible and seeing if reality meets the theory. Which of the following is a good procedure when contacting another station in a radio contest? You have to know what the exchange is and just give the exchange. No chit chat. You're 5-9 Oregon, 5-9 zone 3. And that could be the whole thing. That's a contact. So the minimum exchange. Okay, a grid locator. This is one of those things that I sent out. I'll bring up the grid square map. So the entire world is split up into 324 large grid areas, each of which is 20 degrees wide by 10 degrees high. So 20 degrees of latitude and 20 degrees of longitude and 10 degrees of latitude. And those are given 2-letter combinations. So notice that out in Oregon, I'm in CN. Each of those grid rectangles, if you want to think about it, is split into 100 smaller ones. So there are 32,400 unique rectangles on the planet. And to be honest, to be factual, they're not exactly rectangles. They're more kind of like curved trapezoids because the Earth is curved. But anyway, I digress a little. The reason that we do this is that, let's say that I am in CN 84 and I'm using a very directional antenna, and I hear somebody calling in Montana. Well, look at the heading from my grid square to Montana. It could be in the very northwestern corner, in which case I'd be about a 45-degree northeast heading, or it could be far eastern Montana, in which case it's almost due east. If I have a high gain beam antenna, where would I point without knowing where they are in Montana? So this grid locator map allows you to basically pinpoint a little bit better where somebody is on the planet.
Okay.
Beyond that, each of these is then actually broken up into a 24 by 24 subgrid, which is even smaller. So to be specific, I'm in grid CN84LA. That actually indicates exactly where I am, down to, a 5 by 5 mile block.
like I'm looking, Scott, I'm looking at mine and we're FN 21, 31, 20, and 30. We're right in that corner.
Yeah.
Where would I find the other map to find out exactly where we are?
Well, if you know your latitude and longitude, you can figure it out.
Oh, okay.
It's figured out from your exact latitude and longitude.
Oh, well, okay.
Okay, let's see. So that's grid locators. Which of the following methods is used to locate sources of noise, interference, or jamming? That would be radio direction finding. There are events that are called fox hunts or bunny hunts, where you basically look for a hidden transmitter, it's a really good practice exercise. Basically, if you have a line that says that you're in here, and in here, well, you now have an idea that the hidden transmitter is somewhere in here. We do it with a hidden transmitter that we've put there on purpose. Sometimes it's a hidden transmitter that was not put there on purpose. It's just there because somebody has something that's transmitting incorrectly or maliciously. So we practice so we can know how to find stuff. And that's known as radio direction finding. So what's useful for a hidden transmitter hunt? That would be a 3-element antenna, a directional antenna. That could also be a dish. It could also be something like this. We have many of these in our club. And the reason being that these are wonderful little antennas. This is called a tape measure Yagi. There you go. It's actually made of pieces of tape measure, and it's collapsible because of that. And it's really, really cheap because it's just PVC and pieces of tape measure, and everyone's got a broken tape measure.
You bet.
So there you go. Very easy to build.
The Kettering University.
Yeah, exactly. Oh, do you have one there?
We have several, a couple of which were made before I got there, and then one we finished up during my freshman year just as an activity.
Yeah, we just did a build here at the University of Oregon station at the club. We just had a group build. We built a few more. I think 4 for people to take home and one for the club.
That sounds really fun. Yeah,
Yeah.
Our most current project, we're working on a CubeSat simulator kit.
Oh, cool.
From I can't remember where, but it's a kit with a bill of materials, and it will essentially simulate a CubeSat tumbling through space and everything with the Doppler shift and all that fun stuff.
Cool. So is that the computer science department that's leading that, sort of, or the
No,
computer
it's
science people?
Myself leading it. We found it online, and we're just taking our own initiative to do this.
Oh, cool. You get any credit for it? Does it transfer over at all?
Probably not. It's a club activity, but
Yeah, I
it's
know.
certainly something I can look into.
Yeah, and who knows, it might have a little bit of crossover when you actually come, and it actually comes times to do a project or something.
Oh, absolutely. It at the very least, it's good practical experience to have.
Yeah. Okay, IRLP. What is the Internet Radio Linking Project? It's a technique to connect amateur radio systems such as repeaters via the internet using voice over internet protocol. And we actually do that quite a bit. IRLP.
So is that how like a network of repeaters generally is communicating with each other so that they're all broadcasting the same signals?
For instance, there are some really big repeater systems that are set up all over the world that can be linked together over the internet. Yes. And I'm trying to remember what it's called. We actually have a node here on one of our repeaters. And yeah, it's basically like there are repeaters in Japan and Australia, and they're all tied together over the internet. So voice over internet protocol is a method for delivering voice communications over the internet using digital techniques. So basically, when you pick up your cell phone, you're using voice over internet. Your voice is digitized and sent across the internet as packets. Echolink. Echolink is essentially an internet-based system by which individual hams can send in a copy of your license and your call sign, and you're given an account, and you're basically allowed to access internet-based repeaters. So this is actually, we have that in our club. Basically, if you're a club member and you're whitelisted, you are listed on the on the webpage. And once you have an Echolink account, you can access our repeater through the internet wherever you are in the world. So if you want to use it to check into a net, which we have on the repeater, you can do that from anywhere on the planet. How can you, actually, some repeaters are open to Echolink. So basically anybody with an Echolink account can get into a repeater. So I've actually connected to several, I've spent a lot of time working in Chile, and I've actually connected to several repeaters down there and talked with people in some of the towns where I'd worked. How can you obtain a list of active nodes that use voice over internet protocol? Online repeater lists such as Repeater Book, a repeater directory, or an online service are all good ways to do that. IRLP is, again, the Internet Radio Linking Protocol or Internet Radio Linking Project. How do you access IRLP nodes? Well, if you look at your handheld radio, notice that's got a bunch of numbers, usually used for punching in frequencies. If you've got the push to talk press, those are actually used for sending touchstones. So if you key up the radio and press 226, and 226 is the code for bringing up an Echolink node or an IRLP node, you now have access to the IRLP. That's known as DTMF, or dual tone multi-frequency. That's a touchtone. An amateur radio station used to connect other stations to the internet is known as a gateway. Okay, and we're getting into rules and regs. Rules and regs. This is just stuff that there's no way to do other than memorize. A lot of it is pretty much common sense. But here we go. We're on page 79. The agency that regulates and enforces the rules for the amateur service in the United States
FCC
is the Federal Communications Commission.
FCC.
FCC. Okay. Part 97. Part 97 is the rules. It's, or some TV shows would say, the rules. It's all the rules that govern amateur radio in the United States. And remember, one of the first things we did in this class was I brought up part 97. And part 97, now that you've been through a lot of this, what I'm going to do is go back to the ARRL website. And here's the ARRL website. And notice what this covers: the amateur radio service. There's a lot of rules. This is just the headings. This is just the chapter titles.
Mm-hmm.
And then, but you know, basically, if you have a question, the answer or answers or suggested area that the answer will be in are found in here. So I don't know anyone who's ever read all the rules, but here's all the rules that you're agreeing to. Again, it's not your job to know them. It's your job to know where to find them. Part 97 definition of a beacon. A beacon is a one-way transmitter that's used for observing propagation or experimental activities. And a space station, the limit of space is 50 kilometers up. That's something you have to know. If it's below 50 kilometers, it's a terrestrial or Earth station. If it's above 50 kilometers, it is a space station. When are you allowed to willfully interfere with another ham radio operator?
Never.
Never. You can, because this is a, if you think of it this way, this is an FCC license, right?
Mm-hmm.
But by being FCC licensed, you have the same obligations to follow the rules that, let's say, a commercial TV or radio station does. A commercial TV or radio station, if they do something that's outside the rules, can get fined thousands of dollars. So can we.
Mm-hmm.
It's not that common. We kind of, to a large degree, we regulate ourselves, because to be totally honest, we don't want the FCC sticking their nose in what we're doing. We want them to view ham radio as a self-regulating group. In order to keep that, we basically will police our own. You know, we don't go out and enforce anything. If some, you know, but we will say, hey, you know what, you're operating illegally. You should probably stop because it makes all of us look bad.
Right.
And if it gets really bad, then we get as much information as we can and we give it to the FCC and say, we've done all we can, all yours. And then they'll go figure out who did it. And, you know, depending on what it is, they'll file it in court and they'll put a lien on somebody's house. So they don't play games. Which of the following entities recommends transmit and receive channels and other parameters for auxiliary and repeater stations? Believe it or not, that is not the FCC, because the FCC does not want to be dealing with things like that. The FCC wants to be dealing with cell phones. The FCC wants to be dealing with cable TV systems and things that actually make money. The FCC makes $0 off of us, at least right now, until it becomes $35 to handle a license transaction. But in the grander scheme of things, that's still pretty much zero for the FCC. So they have almost no budget for dealing with us whatsoever. So what does that mean? That means that they really don't want anything to do with us. They say, here are your frequencies, go deal with them. So we have something called a volunteer frequency coordinator, which is made up of a group of people whose job it is. They are essentially named, they're selected or voted in by other hams, and their job is to keep the peace and say, okay, well, these are going to be your repeater frequencies. These are going to be simplex frequencies. And if somebody has a repeater they want to put up and somebody else has a repeater there already, they'll say, okay, well, can we share? Are we too close together? Let's make some maps and figure out if it's going to cause interference. Who selects a frequency coordinator? Amateur operators in a local or regional area whose stations are eligible to be repeater or auxiliary stations. So basically, Valley Radio Club, W7PXL, we are part of the volunteer frequency coordinator. We will elect the frequency coordinator because we have a repeater. You know, when the question comes up, what do we want to do? We have a say because we're part of that group, because we have a repeater. Okay, so the next one, we're now on page 81.
Woohoo!
Somebody had a question? Nope, just an echo. Okay. The ITU, or International Telecommunications Union, and I apologize for not showing. Anything more interesting than the book, but I really don't have anything more interesting than the book to show in this case. The International Telecommunications Union is a United Nations agency. It's part of the UN for information and communication technology issues. They're the ones who decide who gets what prefixes, for instance. You know what? I guess I did have something more interesting to show. So let's see. ITU amateur prefixes. Okay, I did have something more interesting to show. Here we go. Okay, so here are ITU prefixes. These are.
It's under our ham. It's under the band, US band plan.
Okay.
If you scroll down.
Okay, so here is prefixes and who they are assigned to in the world. So basically, if you hear a station with a certain prefix, for instance, V26, you can go here and say V2, that is Antigua and Barbuda. And look, there it is on the map. So you learn a lot of geography this way. Okay, now we're going to look at our frequency chart. Hello, doggy. Okay, we're going to look at our frequency chart. Band plan. Okay. So which frequency is within the 6 meter band? What are the limits on the 6 meter band, everyone?
Oh, 6 meter.
50 to 54.
50 to 54
Megahertz.
megahertz. Right. So I think one of the possible answers could be 49.99 megahertz. That's very close to mathematically 6 meters, but it is not within the band. You have to know the limits on the band. So 52.525 is definitely in the band. And actually, that is the FM 6 meter calling frequency. When you're on 146.52 megahertz, what band are you on?
2 meter band.
You're on 2 meters.
So
except in Europe. If
to
you're
an
in Europe,
extent,
go ahead.
sorry, to an extent, you can just use the frequency, speed of light, and divided by the number of meters to get the approximate frequency, but you don't really know in the calculations alone how big those bands are.
That's right. You have to really know what the bands are. So notice that 146.52 is our FM calling frequency. It's right in the middle of this thing called FM simplex in that pink area. What's interesting is that in Europe, the 2 meter band is 144 to 146. Above that is not a ham band. So when you go to Europe, you have to know that. Why should you not set your transmit frequency to be exactly at the edge of an amateur band or sub band? I'm going to draw this. Okay, so everyone take a look at we're going to look at the 20 meter band, and it ends at 14.350. All right, so it goes from 14.000 up to 14.350. The rules basically state that our entire signal must be inside this bucket. Can we have anything splashing outside?
No.
No. Okay, so what do we know? This is why it's important to understand what certain modulation schemes look like. Let's pick 14.300, and we do upper sideband. How wide is this an upper sideband signal in kilohertz? Upper sideband signal is about 3 kilohertz.
3 kilohertz.
So what is the upper end where our signal is going to end? 14.303 megahertz. Okay. Is our signal legal?
Yes.
Yep. Okay. Okay. Our dial frequency says 14.300. Now, we're going to go all the way up, and let's say we hear somebody calling CQ, and we really want to answer them. And our dial frequency says 14.349. Okay, we're going to draw our signal here. Are we legal or not legal if we transmit there?
Still legal.
We are
Yeah.
not legal.
Not legal.
Not legal. Where is the right end of our signal?
Past
Outside of the
14.35.
Outside.
It's past the edge. It goes all the way up to 14.352, which is greater than 14.350. So this is not legal. And that is why it's important for us to know what our modulation looks like and what our bands look like, because we want to remain legal, and this is an illegal transmission. And every year during numerous different contests, what we get are people who will transmit right there because there's not a lot of other people transmitting there, and they'll still get people answering them. So the people who are calling are operating illegally. The people who are answering them are also operating illegally. And the FCC, we don't really want the FCC to get involved in this, obviously. So what happens is we have something called a volunteer monitoring group that the ARRL puts together. And volunteer monitoring group, their job is basically to listen on the bands and find people who are operating legally and illegally and send them notes accordingly. So basically, if you're doing a good job, you'll get an attaboy. They send a lot more attaboys than, hey, you're a little bit wide or your signal's outside of the band. But that is something that you want to know before the FCC knows, because the FCC is the one that can actually do something about it. You know, it's really better for you to do something about it than have to be told to do something about it. Okay, so why do we not set it at the edge of a subband? To allow for calibration error in our dial. So modulation sidebands don't go beyond the band edge, and to allow for transmitter frequency drift. Over time, your radio might get a little old, and the dial frequency could be off by plus or minus 1 kilohertz. Well, if you put it where you think it should be, well, all of a sudden, maybe you're not anymore. So unless you're absolutely sure that your radio is tightly calibrated, you don't want to get too close to the edge. Okay, limit on emissions between 219 and 220. That is that special band that doesn't even show up on this chart. That shows up on the other chart, which is fixed digital message forwarding systems only. It's the one that sounds, it's the answer that sounds really weird. Okay, on which HF bands the technician operator have phone privileges? So we're going to go back to our band plan and see phone privileges, which would be voice. Notice it says novice and technician voice. It's the blue hatch. And the blue hatch shows up on the 10-meter band. So you have access to voice on the 10-meter band. You also have access to data on the 10-meter band. Notice this where it says the splat says novice and technician. You have access to the red area at the bottom of the 10-meter band, which says CW, RIDI, and data. RIDI again is radio teletype. And yes, people still use it quite a bit. Which of the following VHF and UHF frequency ranges are limited to CW only? Those are these red splotches right here between 50 to 50.1 and 144 to 144.1. Those are actually in the FCC rules, that those areas are only for Morse code. Other than that, there aren't any specific rules about what you can do where. Okay, what is the maximum peak envelope power for a technician class operator on the high frequency bands? So that would be down here on the high frequency bands on, for instance, 10 meters or on 15 meters. Notice you have the green hatch. On 40 meters, you have the green hatched area. On 80 meters, you have the green hatched area for Morse code. You're allowed 200 watts peak envelope power, which is actually more power than I run at my own station, or even have the capability of doing so. So that's actually a lot of power. On the VHF bands, 6 meters and above, unless there are some very specific sections that say you can't, you're allowed to run 1,500 watts, which is another reason why you take this class. And the reason that I say that is we're going to do a little bit of math here, right? Okay, we're going to make a dish. All right, we're going to make a dish antenna with a forward gain of 30 decibels, which is a pretty big dish, but not insanely big. And we're going to have a transmitter which has a 1 watt power output. Okay, so in the forward direction, what is my effective radiated power? What does 30 decibels mean? Everybody?
30,000 watts.
Nope. What is it? What happens every time you get 10? You can break up 30 into
10,000 times.
right. It's 10
times.
plus 10 plus 10 decibels, which is 10
1,000
times
times.
10 times 10. Thank you, Masood. There's 1,000 times. So if you were transmitting with 1 watt, what is the effective radiated power in the forward direction? 1,000 watts.
30.
Right? You
Yeah.
basically in the forward direction look like you're transmitting with a kilowatt. And let's say that you're doing this on 2.4 gigahertz, which is legal. That is as much power as is inside your microwave oven. So, can you hurt somebody with that?
We can.
I think so, yeah. So,
You can fry them.
yeah. So basically, one of the reasons that we take this class, one of the reasons that we do this at all is, are you even limited to 1 watt? How much power are you limited to by
200,
law? How much?
200,
1,500 watts.
1,500. Okay.
Okay, so if you manage to, let's say you're trying to do moon bounce and you're on the 1.2 gigahertz band and you're running, somehow you manage to get hold of or build a 1,500 watt amplifier and you have a 30 decibel gain dish. What is your effective radiated power in this forward direction?
150,000.
I think it's more than that.
1
More
point,
than that.
Oh,
1.5 million.
15,
1.5 megawatts.
Yeah.
1.5 megawatts. You can do some serious damage with that, but it's perfectly legal. Part of this class, part of getting a license and getting licensed is knowing how to do this stuff safely. That is why, even if you never plan on doing anything beyond getting a handheld, I would consider that to be a waste if you never went anything beyond a handheld, but it's certainly your prerogative. You have an insane number of privileges, even with a technician class license, to be able to do stuff like that. So you might as well learn to do it. Which of the following is a result of the fact that the amateur radio service is secondary in all or some portions of amateur bands, such as 70 centimeters? And that is, primary user is the primary user. Others have to not be there. Or if they are there, the primary is the first one on the scene. And if somebody interferes with them, the primary gets the privileges. So that means that since we're secondary, let's say the military starts doing operations in the 70 centimeter band, which they could, because they're the primary user, US government and the military, they could say, hey, we need you to scoot over, turn your repeater off. And you would have to turn your repeater off. Okay, we are now on page 83. Okay, for which license classes are new licenses available from the FCC? Technician, general, and amateur extra. I don't know why it's called amateur extra. A license grant is good for 10 years. Basically, the gold standard for whether or not your license is valid is if it shows up in the FCC database. And you are allowed to have one license grant. I know in Canada, you can have multiple licenses. In the United States, you can have one assigned to you. Proof of possession of a license is that your operator and primary station license must appear in the FCC ULS Consolidated Licensee Database. That is, when you signed up for an FRN, the FRN is what issued you your, the database is what issued you your FRN.
Quick question.
Yep.
So I have my GMSR license. Will that go away when I get my technician?
GMRS is totally separate.
Okay.
Yeah, you can have a GMRS. You can have simultaneously with an FCC license. For an amateur license, you can have a general radio operator's license. You can have a GMDSS maintainer certificate. You can have, they're all separate from each other.
But now being a technician, you don't need the GM license anymore, right?
Well, it depends who you want to talk to. I mean, basically you can have like 5 people, I think, operating under a single GMRS license.
Okay.
So depending on what you're doing, it's still useful.
What does GMRS stand for?
It's a General Mobile Radio Service. It's a licensed, but licensed with like a $70 fee for 5 years. And you basically are given access to GMRS channels, and you can run mobile radios and put up repeaters and things like that. But you're limited just to FM, and you're only allowed to use equipment that is type certified for GMRS. For instance, you can't build your own stuff or anything.
And what do you mean when 5 people can be under you?
That, in other words, like if you get a license, the license is like we have one here in Eugene. It's WQZH 655. We have a group that is the Southeast Neighbors Association, and we have a gaggle of radios and a repeater to use that's owned by somebody else. When we get on and do a test, we are all able to use that single license.
Oh.
It's not an
okay.
individual license, it's a group license.
Wow.
Who can select a call sign under the vanity call sign rules? That would be anyone who has an amateur license can request a vanity call sign. It has to be within the group of call signs that is valid for you. So when I say valid for you, if you have a technician class, that can be a 1x3 or a 2x3. So all United States call signs by the ITU rules have to start with W, N, K, or the prefix AA through AL. Those are the prefixes that we are assigned. So W3, A, B, C. That's a 1x3. It's on 1 on the left side and 3 on the right side. KA7TTL. That would be a 2x3. Those are both valid for a technician class operator. Mine, N7JI, is a 1x2. That's an extra class only. And actually, general class, they all have, technician and general all have the same.
Okay.
There's another one, you can still have an advanced license, and they had access to 2x2s. Extras can also get 2x2s, but like KA1AC, that would be a 2x2. An advanced class licensee can hold that.
Isn't it possible to have a 1x1, so 3 total for CW purposes, a shortened call sign?
No, you can get a 1x1 as a special event. Yeah,
okay.
It's a temporarily holding a special event station.
All right, I thought there was something shorter primarily used for CW, but I must be misremembering something.
Yeah, no, you can do a 1x2. I mean, that's why I have a 1x2. I love my call sign. What is the grace period following the expiration of a license? That would be 2 years. So if it expires within 2 years, you can get it back. But you're not allowed to transmit while it's in grace period.
Right.
A club has to have at least 4 members to be considered a club and apply for a call sign. If the FCC tries to mail something to you and it gets returned as undeliverable, this means always keep your mailing address current because they can pull your license. When are you allowed to operate in a foreign country? That's whenever the foreign country authorizes it. And you're allowed to operate from any United States flagged ship or boat in international waters registered in the United States, so long as the captain says okay. What are the restrictions concerning transmission of language considered obscene and indecent? That's prohibited. Basically, if you wouldn't say it to a 7-year-old, don't say it on the air. Under what conditions is an amateur station authorized to transmit music using a voice emission or phone emission? This came out of the days of the wake up message, the wake up music for the astronauts, where we would be retransmitting space shuttle communications, and part of that would be a wake up message in the form of a song. That's the only time we're allowed to transmit music. We have plenty of other stations that do music transmission. When can you transmit messages encoded to hide their meaning? Again, that's if you're talking to a remote control craft or to a space station like a satellite, so that you don't, accidentally crash. Somebody doesn't take it down. When are we prohibited from exchanging communications with another ham or a country? There are no such conditions right now that exist with the United States. Even North Korea, if there was a licensed North Korean ham, North Korea and the United States have not told the ITU that we're not allowed to do that. There are a couple of countries in the world that are technically still at war. There was a group of hams that went to an island off the coast of Oman, or was it Yemen? I think it was Yemen. And they were not allowed to contact Israelis and vice versa, because they're technically still at war and have been for the last 59 years. So they were not allowed to, they were prohibited from contacting each other. They could hear each other, but they couldn't contact each other. In which of the following circumstances can the control operator of an amateur station receive compensation? Remember, I said we were a non-commercial voluntary service, right?
Right.
No pecuniary interest, meaning no money. The only time you can make money is if you work, for instance, for W1AW, which is the ARRL, and you do code practice as part of your job, or more importantly, when it's incidental to classroom instruction. So that means if I am paid to be a teacher and I am a licensed ham, I can use my license as part of education. So I can actually teach ham radio and still receive my salary. When can amateur operators use their stations to notify other stations of the availability of equipment for sale? If you don't run a business and it has something to do with a ham radio station. I'm selling a perfect chair for an operating position. That's maybe okay. I'm selling a radio. Yeah, that's great. I sell radios for a living, not so okay. Broadcasting is transmissions intended for the general public. This is very similar to, but different to something called one-way transmissions. Broadcasting is meant for the general public. One-way transmissions are meant for use in the amateur radio service. In other words, code practice or informational bulletins that most in the general public wouldn't care about, but hams do. That would be a one-way communication. At certain times, if there's an emergency, we're allowed to transmit for information for commercial services like news gathering organizations, television stations, assuming that the cell phones don't work and there's no other way to do it. So there's those two things again that'll always come up. Immediate safety of human life, protection of property. Those are always the correct answer. Safety of human life, protection of property. So basically, if either of those things comes up, you're allowed to break the rules. You'll have to explain later why you broke the rules. But if you have a valid reason to say the dam was going to break, if you have safety of human life, protection of property, that's a good excuse. How can an amateur radio station make a one-way transmission? Again, a one-way transmission is different from a broadcast. It can be used for beacons, emergency communications, saying, "Hey, Interstate 5 is closed at mile marker 229." You're not expecting a response. It's just for the general public who are hams. So code practice, information, or emergency communications are for one-way transmissions. So what is allowed? The rules, the FCC rules specifically say communications incidental to the purposes of the amateur radio service and remarks of a personal character. Oh, my back is killing me. When are you having that surgery? You know, you hear that a lot. And I used to think that was really funny, except now I'm 52 years old and I understand it. Anybody else in that boat? Oh,
Yeah.
God, I woke up so sore.
I'm getting that at 20, unfortunately. So,
all right, we're in the very last section, control operator and control types. And for that, what I'm going to do is grab a hold of my handheld. Okay, there must be a control operator available for every station that's transmitted. There must be a control operator. I am the control operator because I am holding this radio. Who is the control operator? Unless there's documentation otherwise, that would be the licensee of the station. Now, I could designate somebody else as the station as the operator if I wanted to. So let's say, let's see. Who is responsible for proper operation of a station? There are two people. There's a station licensee and a control operator. If I'm the owner of the station and somebody comes to visit and they're a ham and I say, you can use your call sign, feel free to operate. If something goes wrong and we interfere with aircraft, it's both of our fault because they were the control operator and I'm the owner of the equipment. So it's both our faults. So if a repeater inadvertently retransmits communications, somebody gets on a repeater input frequency and starts cursing, I feel bad about it. I would try as the owner of the repeater to shut it down, but it's not my fault. Whoever actually, because it's an automatic station, whoever initiated the communications, it's their fault. What determines the transmitting privileges of an amateur station? Okay, so Quinn, let's say that you've got your club call sign, right? Okay, so you've got your club call sign.
I hear you.
Do you presently hold a ham license?
Not at the moment.
Not yet. Okay, so somebody walks out and says, you can keep operating. Can they say that? If you're the only one
I
there?
don't believe so.
You cannot. There has to be a licensed control operator there. So let's say you get your technician class license and the person who was the control operator had an extra. And they said, I'm going to go walk out and get a Coke. Can you keep operating as an extra class licensee?
Not at the extra level. I would have to move frequencies to
That's right.
technician level.
That's right. Basically the license, the class of operation of the station is equal to that of the control operator, and that's it, no higher. So can a control operator be a technician? Yes. Can a control operator be a technician and be operating in a band, in the extra class band? And the answer is no. So it's actually really simple, but it's just kind of a pain to deal with. Local control, remote control, and automatic control. Okay, the control point is the point from which control occurs. In this particular case, it is the push to talk button on my radio. It is my own hand. That is the control operator function. I am the control point. Automatic control would be a repeater or an auxiliary station or a space station that's just retransmitting stuff. Remote control would be operating something over the internet. There are in the world of ham radio, lots and lots of ways to control a radio over the internet now. You have to actually be at the computer. If you walk away from the computer, you are supposed to shut the system off and not have it operate without you being there, because the rules say that a control operator has to be present. So basically, if your radio is operating remotely, somebody has to be at the controls. All right. So which of the following are true of remote control operation? You can control it indirectly. A control operator has to be there, and a control operator has to be at the control point, which is the keyboard on the remote computer. Okay, here we go. Very last section. How often do you transmit your call sign? Everybody.
Every 10 minutes and at the end.
Every 10 minutes and at the end. Okay, when is the only time you're allowed to transmit without a call sign? There's only one. And that is if you're using a remote control craft. Remote control, RC car, RC plane. And in lieu of that, you actually, on the transmitter, you actually have your call sign typically engraved with your address and your phone number on the act and with your call sign.
Hey, quick question there.
Yeah.
If, extreme scenario, but I'm lost in the desert and I lose track of someone.
You can use any means necessary. Any means necessary. You might have to explain, but I found a radio. I've got my radio. I can transmit on the police frequencies. Oh my God, I'm about to die. Nobody's gonna complain.
And basically, if it's an emergency and it's a viable emergency, you can do whatever you need to do to survive.
Yep.
Scott,
Awesome.
real quick
Thank you.
question.
Yes.
What, now you said you have to be present on a remote.
Yep.
But how does that apply to like a room or a node?
If you're doing it over the internet, you have to be there. I mean, I think a node, something that's automatic would be automatic. It wouldn't be remote. Okay, what language can you use?
Can you explain the reason why you don't use a call sign on a control model craft? Is it because you're not really using voice? You're just using some other frequency?
Well, yeah, and nobody's listening. They're not. I mean, if you buy like a Futaba controller, you can have it on the ham band, but it's not really designed to set up a call sign, and it doesn't really achieve anything. And you're limited to 1 watt of power, and usually on the 6 meter band. That's typically the band that's used for remote control. So it's one of those special cases where people started using the ham band for remote control because they had a ham license and they could get a commercially available transmitter. and move it. Okay, what language are you allowed to use to identify in the United States?
English language.
You can have your whole conversation in Spanish, but you have to identify in English. Now, when I went to South America, I could have my whole conversation in English and I had to identify in Spanish, exactly. Had to follow the rules of that country. How do you identify your station transmitting voice? You can do it by saying your call sign, N7JI, or you can use Morse code or CW and do it in the background. Phonetics are encouraged. They remove a lot of ambiguity. If you're using a tactical call sign, for instance, race headquarters or aid station 3, how often do you have to give your own call sign and identify your station? What do you think, everybody?
Every 10 minutes and at the end.
Every 10 minutes and at the end. In other words, you can call yourself whatever you want. You can say I'm aid station 3, but that's not your call sign. Okay, here we go. Slash, operating portable or mobile. You can, when you speak it, you can say I'm N7JI slash W3 or N7JI stroke VE6 or N7JI slash. So basically there are 3 options: stroke, slant, and slash. They basically all indicate a slash sign. That's how you operate portable somewhere. All right, third-party communications. If I'm communicating with, let's say, Bob, and I am relaying a message from somebody here to Bob, I would be the first person, Bob would be the second party, and then the third party would be the unlicensed person for whom I'm sending the message. Now, Bob could also hand it off to another unlicensed third party. So I could actually pass a radiogram from somebody who doesn't have a license to somebody else who doesn't have a license through another ham. That's known as third-party communications. We are only allowed to do third-party communications with countries that the United States has an agreement with. And that is to basically protect the long-distance companies and the nationally owned telecom companies. So like Europe, Japan, we don't have third-party agreements because their telecom companies historically were owned by the government. So why would they want to take money away from themselves?
Where can we find a list of countries we have that agreement with?
That is easily found on the ARRL website. You can say just third-party agreement, US third-party agreement communications, ARRL. And finally, if the FCC comes to your door and says, open up, we need to look at your equipment. We know you've got a license. You should probably open up the door and let them look. And that's the whole thing, everybody.
Do they have to show special FCC identification?
Well, I don't know anybody who that's ever happened to, but not personally, but probably. So notice this list of third-party agreements. Oddly enough, Cuba is on the list. You know, we're not necessarily friendly with Cuba, but you'll notice there are virtually no European countries. And
the UK down there.
The UK, but only these GB stations. And there are only a few of those. You can't just use all hams. Like any United States ham can pass traffic with the third-party traffic to any other US ham or any other Canadian ham and vice versa. Or any of these countries. And notice a lot of them are in South America, and a lot of them don't really, and historically did not have very well-developed telephone systems. So this was actually really helpful for them. All right, and that's all I got, everybody.
That's
all, folks.
Well, I hope that was okay. I know it's a lot.
Great job. Thank you very much.
Thank
Yeah,
you.
you're awesome, Scott.
For walking us through all of that.
It was absolutely amazing. I think I have 15 pages worth of notes or so.
Okay. And
I beat that by about 10.
And you know, the thing is that this is really just to get you started. what you really start to learn when you actually get on the air and start doing things. And what you'll find, somebody in our club recently said, I wonder if I made a list of all the different areas that I could go into in ham radio. I wonder if I could make a list. So they list, antenna design and building and operating and emergency communications. They came up with a list of 52 different areas. And they just looked at it and said, even if you started to go into it and went semi deep into each one, you could spend a year really getting to the point where you really understood what was going on and became an expert. And there were 52 different areas that they could just come up with off the top of their head. I mean, people say that this is you can try something in ham radio and try something new all the time and never run out of things to try. And I really do think that's true. So don't limit yourself, I guess is what I'm saying. Don't just get a radio and say, I'm just going to keep this for emergencies, charge it up and then throw it in the drawer. It's something that you've earned the privilege to use this, and you might as well learn to use it and really, get everything out of it that you can.
My wife might disagree with that.
Oh, she's tired. Wrong.
She's tired of seeing, I'm on tower number 4 and,
oh, wait, you have 3 towers already?
Yes.
I have none.
Oh, no.
I've never had a tower.
Well, I've got 15 acres and she says that I have to fill up every inch of it.
Oh, well, cool.
Yeah.
Have you put up any large loops yet?
No, I have not.
Okay, well, if you've got 15 acres, you can do some serious stuff on 160. See, I have a city lot. I can't really operate on 160 very well. That's the only band on HF for which I have not got a Worked All States award.
Wow.
And what I'm finding is that 160 is really freaking hard.
And you don't have a tower because of limitations of space, or?
Yeah, there's no real place to put it here. I've got lots of huge trees. I mean, I've got 120-foot trees, but I don't really have any good place to put up a tower, and I don't think my wife would really appreciate it. And to be honest, I don't think I'd want to maintain it either.
Mm-hmm.
I wouldn't want that hanging over my head, literally.
Yeah.
I'd rather have stuff that I can just shoot up in the trees. But at the same time, there are a lot of days that I wish I had some really big antennas up there and could compete with some of the guys in Central Oregon who've got, 50-foot tower and they live at 4,000 feet outside of Sisters. And there's this one guy, W7YAQ, who I can never beat in any contest unless he enters a different category.
Uh-huh.
I have so many second place trophies.
Wow.
Which is a piece of paper.
Yeah, but still.
So, all right. Well,
I at one point had a tower that was originally for satellite TV.
Mm-hmm.
And it went unused, and like literally 5 years before I even thought about getting into this, I accidentally hit it with a tractor and tipped it over. That is one of my bigger regrets.
But was it in concrete?
It was in concrete.
You knocked it over. Wow.
No, well, I basically cut one of the beams and it collapsed on its side. So it didn't rip out of the concrete. We had to grind down the sharp bits sticking out of the concrete.
Yeah, that sucks.
Yeah, it was unfortunate. We got like a 7-foot grounding pole out of it though. So
yeah,
we can always set it up somewhere else.
All right. Any other questions, everybody?
Are there particular brands that you recommend? So I'm doing like backcountry work with the ski patrol. Are there particular brands or styles of two-ways that you recommend?
I mean, really, one question to ask is, do I want the same radio for amateur and ski patrol use?
We're working on commercial bands on the ski patrol, and so the average ham amateur unit isn't gonna work.
However, some do. There are some of these radios that are type 90 accepted. There are some handhelds that have a type 90 acceptance, which
Yeah,
makes
and
them usable.
we have some for the patrol, and Stephen, I can get you in touch with the right way to get a hold of one of those.
Yeah.
It gives you
Okay.
access to the ham bands and the commercial bands.
Cool.
Yep.
Thanks, Rosie.
Yep, indeed.
Scott,
Yeah.
where are you gonna post, where are you gonna post this for viewing?
It'll be on YouTube once I get everything figured out.
What's the
Okay.
channel?
Hmm?
What will the channel be?
I'm just gonna send out the link.
Oh, through the email?
Yeah.
Okay, good.
Thanks, Scott. Thanks a
All right.
lot.
Thanks, everybody.
So do you do a lot of field trips? Like I see your one there that where I signed up was you're in, I think West Virginia. I saw 2016 maybe or something.
I travel, I do a lot of work in sawmills. So wherever there's wood, wherever there are a lot of trees, I go there. So, yeah. So this coming fall or this coming winter will be Idaho, Montana, and North Carolina at a minimum, and probably somewhere in probably like Grand Prairie, Alberta.
So you were doing like work through your business as an electrician, as a diagnostic?
Actually, electrical and controls engineer.
Oh, controls, you said, yeah.
Yeah. So a lot of, we do all the machine building and design in our shop, and then they send me out as well as the person who did the design to go and start it up.
So when you were in West Virginia, you were there for business, but
2016.
Decided to do a ham field trip type thing.
Well, I always take my portable stuff with me if I have room and I remember and have enough time.
That's
So
cool.
I take portable equipment, and so I knew I was going to be there over field day, and field day is a big, nationwide outdoor event. And thought to myself, well, I'm gonna haul it all with me and threw it in the suitcase, and the time worked out that we were done, and I had a couple of hours that I could devote to it. I missed most of it, but I worked all weekend and still got to operate a little bit.
You don't have problems carrying all that if you're flying?
I mean, you just can't check a battery.
Yeah.
That's it. I put my QSL card in there with it. That way, if anyone says, "Oh, what's all this stuff?" They look at the card and it's got my name and call sign on it, and eventually somebody will figure it out, and they just, put it through the X-ray machine like everything else.
Okay.
I've gone
Hey,
all
Scott,
all over Europe and South America with it.
With a tower, why would you want a GPS antenna? What does that do?
I have no idea.
Yeah, I just saw that the other night.
I have no idea, unless you're doing APRS with it.
Yeah.
But, I don't know.
I'll do more research.
So
Thanks for everything.
After we pass our test, locally in Eugene,
yep.
How do we find mentorship to build our skill set and better understand how things are working and how we can improve our setups?
Well, here's the easiest way. Local clubs. Here we go. Valley Radio Club, of which I'm the trustee, and we have meetings on the air every month now until we can meet again in person. And I mean, notice this list of stuff. These are weekly things that we do on the right-hand side. So notice there's something Monday, something Tuesday, something Wednesday, something Thursday, and something Friday, and then Saturday, and then Sunday. So there's literally something to do every day. Just depends how into it you want to get. We have a repeater with really good coverage. I mean, it covers all the way out to the ocean, all the way to the mountains, and all the way up to Salem and part way down to Roseburg.
That W7 RXL?
PXL. Papa X-ray Lima. I think at last check, we were up over 150 paid members, which is amazing.
Do you have frequencies that you like to go to on a regular basis that are solid, or
For what?
to check in, see if anybody's there to talk to?
Well, I mean, you're talking locally or on HF or
Yeah, HF.
not really.
Okay.
I mean, I'm really a DXer at heart. So whatever bands are open, that's where I'll be.
Okay.
So how do we find a local club to us?
Okay, let's see.
ARLL.
And where,
ARRL.
ARLL?
ARRL.
Yeah.
Here. And clubs.
Okay, I see it.
Search for ARRL affiliated clubs. There are only 2,782 of them.
Wow.
Okay. So there might be one in northeastern Oklahoma.
Let's see.
Deborah, there's several actually. There's a Rogers County Amateur Radio Club. There's a Mays County. There's a Craig County. We've listened to several of them in the area here.
Cool.
There's 38 in the state of Oklahoma these are just ones that are affiliated with the ARRL. This is not necessarily all of them. And some are more active than others. You'll find some have, special interests, but yeah, like Oklahoma DX Association, that would be contesting and DX. So if you're interested in that, that's what you get into. But yeah, you notice there's a lot.
DX
Awesome.
Resistance.
Guy here, because he suggests not cram for it, but
So
Thank
and
you.
notice some are like special service clubs, some are just AR affiliated. But yeah, and the other thing, of course, that I always recommend is to join ARRL, as it's basically our voice, our collective voice when it comes to legislative issues. They're our, 160,000 paid members. When they go talk to Congress or the FCC, it has a little more weight than just, a couple of people writing a letter. So, and they do a lot of educational stuff. Like if you found this class on the ARRL website, they also administer scholarships, Quinn.
That's one of our main selling points, trying to get people to join the university club, is scholarships.
My daughter, who you'll meet at our exam session, she actually got a $25,000 scholarship this year.
Wow.
Yep.
That's incredible.
Yeah. Yep, I can actually say that. So she got a $25,000 scholarship.
That's awesome.
That's,
Congratulations.
yeah, thank you. It's an entire year of education. All right, I'm gonna go and grab something to eat, and I'll see you guys at this exams.
Okay, thanks
And if
again.
you're not coming to the exam,
Thanks, Scott.
see you around.
Thanks, Scott.
Feel free to ask questions and stuff. I know you'll probably have some.
Thanks, Scott.
All right.